Hello there, and welcome to the Cosmographer. About 5,000 light-years from here, there is a cloud of gas sitting at 1 degree above absolute zero, colder than empty space itself, colder than the leftover heat of the Big Bang, and the only place in nature known to have managed it. Tonight we count down 20 objects like that, 20 real, catalogued, photographed things sitting on the wrong side of a rule astronomers had already written down. A planet whose daylight side runs hotter than most stars in the galaxy, where hydrogen is torn apart every morning and put back together every night. A body 5 times the width of the Earth, made of crystallized carbon that used to be a star. A neutron star that takes 6 hours and 40 minutes to turn around once, stopped almost dead by the part of its own explosion that failed to escape. And at the very top of this list, something so extreme that our own instruments looked straight at it for 44 years and reported nothing unusual. Not one of these is speculation. Every one has a catalog number and a discovery date. Get comfortable and settle in. If you would rather fall asleep learning 20 things you have never heard of than 10 you already know, a quiet like and subscribe genuinely helps this channel reach more curious minds like you. Because by the end of this countdown, the reason all 20 went unnoticed for so long will be the most unsettling part of the whole list. Let's begin at number 20. Number 20. The asteroid that wears rings. There is a particular kind of unsettling that has nothing to do with danger. It is the feeling you get when something you were certain about turns out to have an exception, and the exception has been sitting there the whole time, catalogued and photographed and filed under the wrong heading. That is what this list is made of. 20 objects, all of them real, all of them confirmed, and every one of them sitting on the wrong side of a line that astronomers had already drawn. In each case, the rule came first. Someone worked out the physics, established the limit, wrote it into the textbooks, and taught it to students for a generation. And then somebody pointed a telescope in the right direction at the right moment, and the universe produced something that the rule said could not be there. None of these are theories. None of them are speculation about what might exist somewhere. Every object on this list has a catalog number, a discovery date, and a set of measurements. Some of them have been photographed for 70 years. And almost none of them are the objects that usually appear on lists like this one, because the familiar ones have been explained, and the ones that have not been explained tend to be quiet, obscure, and buried in survey data that nobody had a reason to look at twice. So we are going to take the long way through, from number 20 down to number 1, and by the end of it, the pattern that connects them should be clear enough to sit with. Let us begin with something small. Rings, as a general rule, belong to giant planets. That was the understanding for a very long time, and it was a reasonable one. Saturn has them, spectacularly. Jupiter, Uranus, and Neptune have them too, thinner and darker and harder to see, but present. 4 ringed worlds in the solar system, all of them enormous, all of them gas or ice giants. The pattern seemed to be telling us something straightforward. It takes a large body to hold a ring system in place, and it takes a large body's tides to keep the ring material from clumping together into a moon. Chariklo is not a large body. Chariklo is a rock about 250 kilometers across. It belongs to a class of objects called centaurs, which are icy bodies on unstable orbits between Jupiter and Neptune. They are named for the half-human, half-horse figures of Greek myth, because their behavior is a hybrid. Sometimes they act like asteroids, sometimes like comets. Chariklo was found in 1997 by James Scotty, working with the Spacewatch survey in Arizona. It is the largest centaur known. It takes about 63 years to complete one orbit around the Sun. Its surface is dark, made of ice and organic material. For 16 years, that was the entire entry. There was no reason to think otherwise. On the 3rd of June, 2013, Shrapnel passed in front of a faint star. Events like that are called stellar occultations, and for small distant objects, they are enormously valuable, because they are one of the only ways to measure the size and shape of something too small to see as anything but a dot. You time how long the star disappears. Do that from several places at once, spread across different latitudes, and each observing site measures a slightly different chord across the object. Put the chords together and you get a silhouette. Felipe Braga Ribas of the National Observatory in Rio de Janeiro organized the campaign for that night. 7 separate sites across South America, from Chile to Brazil, all pointed at the same star, all timing the same brief disappearance. What the telescopes recorded was not what anyone had planned for. Before Shrapnel arrived, the star blinked twice. Then it vanished behind the rock, as expected. Then it reappeared and blinked twice more. 2 symmetrical pairs of dips, one on each side of the main event. There is only one natural structure that produces that signature. 2 narrow, dense rings, orbiting a body 400 times smaller than Saturn. The rings were given formal designations and informal names as well, after the northernmost and southernmost towns in Brazil. The inner ring is about 7 kilometers wide and orbits roughly 391 kilometers from Shrapnel's center. The outer ring is about 3 kilometers wide, at around 405 kilometers. The gap between them is about 9 kilometers. Those numbers are difficult to picture, so here is a way to hold them. If Shrapnel were the size of a dinner plate on a table in front of you, the 2 rings would be hairlines drawn about half a plate width out from the edge, and the gap between them would be roughly the thickness of a pencil mark. That is the scale of the structure that 7 telescopes detected from a shadow lasting less than a minute, from a distance of well over 1 billion kilometers. This was the 5th ringed body ever found in the solar system, and the first one that was not a giant planet. And it broke the pattern the other 4 had established, because Shrapnel has almost no gravity to work with. Its escape velocity is somewhere around 120 meters per second. A well-thrown baseball would leave and never come back. The problem is not really how the rings got there. There are reasonable ideas about that, mostly involving a collision that threw up debris or the disruption of a small satellite. The problem is why they are still there and why they are so sharp. A narrow ring, left to itself, spreads out. The particles in it collide with each other, exchange momentum, and diffuse inward and outward. Within a few thousand years, a structure 7 kilometers wide should smear into a broad, indistinct disk. A few thousand years is nothing. Shrapnel has been in the solar system for billions of years, and even its current orbit is millions of years old. Something is holding the edges. The candidates are all interesting. There may be tiny undetected moonlets orbiting alongside the rings, shepherding the particles the way small moons do at Saturn. The inner ring may be dense enough that its own self-gravity does the work, keeping the particle orbits aligned so the ring precesses as a rigid structure rather than diffusing. And there is a resonance. The rings sit suggestively close to the distance where a particle would orbit once for every 3 times Shrapnel rotates, and resonances are very good at holding structures in place. The discovery also explains something that had been sitting in the records unexplained for over a decade. Between 1997 and 2008, Shrapnel's brightness rose and fell in a way that nobody could account for. The rock was not changing. Once the rings were known, the answer was immediate and obvious. The rings were changing their angle relative to Earth. Sometimes they presented a wide reflective face, and sometimes they turned nearly edge-on and almost disappeared. It is exactly what Saturn's rings do over the course of its orbit, and astronomers had been watching it happen at Shrapnel for 11 years without knowing what they were looking at. If you gathered both rings together into a single object, the result would be a moonlet only about a kilometer across. That is the entire mass involved. Everything strange about this object comes down to a kilometer's worth of ice and rubble, spread into two hairlines, holding a shape it has no obvious right to hold. There is one more detail that changes the character of the whole thing. On the 18th of October 2022, the James Webb Space Telescope watched Chariklo occult another star. It was the first stellar occultation Webb had ever attempted, and the geometry worked out almost perfectly. The shadow of the rings crossed the telescope's line of sight. Webb's spectrum showed crystalline water ice. Not the amorphous, disordered ice you would expect on something that has been sitting in radiation for billions of years, but the ordered crystalline form. Crystalline ice in that environment does not last. It gets broken down. Finding it means the ring particles are colliding and resurfacing continuously, right now. The rings are not a leftover. They are being maintained. And Chariklo turned out not to be alone. In 2023, rings were confirmed around the dwarf planet Quasar, orbiting at more than 7 times the body's radius, well outside the distance where the standard calculation says ring material has to clump into a moon rather than stay a ring. Chiron, another centaur, has shown occultation features consistent with rings since 2015, and follow-up work suggests that system is actively changing. So the exception became a category. What was, for a few years, one strange rock with 2 hairlines around it is now a recognized class of small ringed bodies, and the textbook rule about which objects can carry rings has quietly been rewritten. But rings on a rock are only strange because we already knew what rings were for. The next object on this list breaks something we thought we understood about how stars end. Number 19. The planet that should have been swallowed. Stars die in a sequence that is well understood, and one part of that sequence is a problem for anything orbiting nearby. A star like the Sun spends most of its life burning hydrogen in its core. When the hydrogen there runs out, the core contracts and the outer layers expand enormously. The star becomes a red giant, swelling to many times its original size, and anything orbiting inside that new radius is engulfed. It is not a gentle process. A planet inside a stellar atmosphere experiences drag, loses orbital energy, spirals inward, and is torn apart and absorbed. Eventually, the star ignites helium in its core, contracts back down, and settles into a smaller, stable state. That sequence is not a guess. It has been observed. In 2023, astronomers reported watching a star engulf a planet directly, a brief flash of light as a world was swallowed, about 12,000 light-years away. The models were confirmed by the event. Which brings us to a star called 8 Ursae Minoris, about 530 light-years away in the constellation of the Little Bear. 8 Ursae Minoris is a red giant, and it is in a specific, well-defined phase. It is burning helium in its core, which places it in what astronomers call the red clump. Stars arrive at the red clump by exactly the route described above. They expand to a maximum size, ignite helium, and contract. The models for this particular star are specific about the maximum. At the tip of its expansion, 8 Ursae Minoris would have reached a radius of about 0.7 astronomical units, 70% of the distance from the Sun to the Earth. In 2015, a team using the Bohyeonsan Optical Astronomy Observatory in South Korea announced a giant planet orbiting that star. It was later given the name Halla after a shield volcano on the island of Jeju. The star itself was named Baekdu after a volcano on the Korean mainland. Halla is at least 1.5 times the mass of Jupiter. It orbits its star once every 93 days at a distance of 0.5 astronomical units. half the Earth-Sun distance. Around a star that expanded to 70% of the Earth-Sun distance. The planet is sitting inside a volume its star used to occupy. It should have spent a long stretch of time submerged in stellar atmosphere. It should have been dragged inward and dismantled, and the star should carry the chemical evidence of having consumed it. Instead, the planet is there, in a nearly circular orbit, going around on a 93-day schedule as though nothing had happened. The first and most sensible response to a result like that is to suspect the result. Red giants are large, turbulent, pulsating objects, and their surfaces can produce signals that mimic an orbiting planet. Plenty of claimed planets around evolved stars have evaporated on closer examination. So in June of 2023, an international team led by Mark Hahn, then at the University of Hawaii, published a careful test of exactly that possibility. They used the Canada-France-Hawaii telescope and NASA's Transiting Exoplanet Survey satellite. They measured the star's own oscillations, the internal ringing that reveals what a star is made of and which evolutionary path it actually took. And they compared radial velocity measurements taken 13 years apart, using different instruments on different continents. The signal held. Same period, same amplitude, same circular orbit, across 13 years. It is not stellar noise. It is a planet, and it is where a planet cannot be. The shape of the orbit is part of the evidence, and it is worth pausing on. Halla's orbit is very close to a perfect circle. Its eccentricity is near zero. That matters because the obvious alternative explanation, that the planet was captured or flung inward from somewhere further out after the star had already finished expanding, would leave a signature. Objects that arrive violently arrive on stretched, elliptical paths, and it takes a long time for those paths to round out. A circular orbit is the signature of something that either formed where it is or has been there long enough to settle. Neither of those options is comfortable for a planet inside a former red giant. The asteroseismology was the other half of the case, and it is a remarkable technique. Stars ring. Sound waves travel through their interiors and reflect off their surfaces, producing tiny brightness variations with characteristic frequencies. Those frequencies depend on the density structure inside the star, which means that by measuring how a star flickers, you can determine what its core is doing without ever seeing it. Tess watched 8 Ursae Minoris flicker, and the frequencies confirmed the diagnosis. This is a core helium-burning star. It has already been through the phase that should have destroyed its planet. 2 explanations have survived scrutiny, and both are strange in their own way. The first is that 8 Ursae Minoris was never a single star. If it began as a close binary, 2 smaller stars orbiting each other, then those 2 stars may have merged before either of them had the chance to expand into a full red giant. A merger of that kind can send the resulting object straight into helium burning, skipping the enormous expansion phase entirely. On this reading, the giant phase that should have consumed Halla never happened at all. The star's chemistry offers some support. Certain elemental abundances are consistent with an object that took an unusual route to where it is. The second explanation is stranger. Halla may not be a survivor at all. It may be a second-generation planet, formed after the merger, out of the debris the collision threw off. 2 stars collided, some of the wreckage settled into a disk, and out of that disk, a new Jupiter-sized world assembled. And on that reading, Halla is younger than the star it orbits, and it is made of the remains of a stellar collision. Second-generation planets are not an invented idea to fit an awkward case. The very first exoplanets ever confirmed, back in 1992, orbit a pulsar, and they are thought to have formed from the debris of the supernova that made it. Planets can be built out of stellar wreckage. It has happened before. The question has not closed. In 2024, the case was reopened, with fresh scrutiny of whether a triple star history or a different evolutionary path might reconcile the numbers more cleanly. What has not changed is the core observation. A Jupiter-class world sits comfortably inside a region a red giant occupied, and the models used to predict planetary engulfment have to account for it. That matters beyond one system, because those same models describe something closer to home. In roughly 7.5 billion years, the Sun will reach the tip of its own red giant branch. Calculations published in 2008 put its radius at that point at around 256 times its present size, which carries it past the orbit of the Earth. Every account of that ending assumes the planet does not survive the contact. Haller does not overturn that. But it is a real object, measured across 13 years, sitting in exactly the place where the assumption says nothing should be. It is estimated that about 1 in 10 Sun-like stars will engulf a close-in planet at some stage, which makes the number of survivors a genuine prediction rather than a curiosity, and the survivors, if there are more of them, are out there to be counted. That planet survived a star that grew too large. The next one has the opposite problem. Its star never grew at all, and it is hot enough that being close is the entire story. Number 18. The planet hotter than most stars. The line between a planet and a star is usually easy to draw. Stars fuse hydrogen and produce their own light. Planets do not. Stars are hot because of what happens inside them. Planets are warm, at most, because of what happens to them. That line holds almost everywhere. There is one world where it becomes uncomfortable, and it is called Kelt 9b. The discovery came in 2017 from a team led by Scott Gowdy at Ohio State University, working with an instrument whose name is a small joke at its own expense. The kilo-degree extremely little telescope is, in fact, extremely little. Its lenses are about 42 millimeters across, smaller than the finder scope on many amateur telescopes. The design is deliberate. Very bright stars saturate large professional instruments, so a survey that wants to watch the brightest stars in the sky for planetary transits is better served by something small. What that small instrument found sits about 670 light-years away, and it is the hottest planet ever discovered. The reason is the star. Kelt 9 is an A-type star, with a surface temperature around 10,170 Kelvin. That is roughly twice as hot as the Sun. It carries about 2.5 times the Sun's mass, and it is enormously more luminous. Stars like that were not expected to host close-in giant planets at all, because their output should scour their inner regions clean long before a planet could settle there. Kelt 9b orbits that star once every 35 hours. Its dayside temperature is around 4,600 Kelvin. That number needs a moment, because on its own it means very little. Here is the comparison that makes it land. 4,600 Kelvin is hotter than the surface of roughly 80% of the stars in the galaxy. The most common kind of star in the universe is a red dwarf, and a red dwarf's surface runs at about 3,000 Kelvin. So the daylight side of this planet is around 1,500 degrees hotter than the surface of a typical star. If you could somehow place Kelt 9b next to an ordinary red dwarf, the planet would be the hotter of the two objects. At those temperatures, chemistry as an atmosphere normally understands it stops working. Water cannot exist there. Carbon dioxide cannot exist. Methane cannot exist. The molecules that make up every planetary atmosphere we know are simply pulled apart by the energy in the environment. And then it goes further than that. Molecular hydrogen, two hydrogen atoms bound together, the simplest and most robust molecule there is, the substance the planet is mostly made of, is torn into individual atoms on the day side. What happens next is the part worth holding on to. The atomic hydrogen circulates around to the night side. The night side, while still extraordinarily hot, is cool enough that the individual atoms can find each other and bond back into molecules. Then the circulation carries them back around into the daylight, where they are ripped apart again. The planet runs a continuous cycle of molecular destruction and reassembly, day side to night side and back, and the energy absorbed and released by that cycle is itself one of the main things governing how heat moves around the world. There is a boundary somewhere on that planet, a line running roughly along the terminator, where day meets night, at which hydrogen changes what kind of substance it is. Cross it going one way, and you are in a gas of molecules. Cross it going the other, and you are in a gas of individual atoms. The line is not sharp, and it moves, and it has been doing this for as long as the planet has been where it is. The planet's physical shape reflects all of this. Kelt 9b carries about 2.8 times the mass of Jupiter, but it has nearly twice Jupiter's radius. It is severely inflated, puffed outward by the sheer quantity of energy it is absorbing, held in a distended state it could never maintain further from its star. Its density is correspondingly low for something so massive. It is also, in an unusual sense, glowing. Most planets are visible only by reflected light. They shine because a star shines on them. Kelt 9b is hot enough that a substantial fraction of the light coming from it is its own thermal emission, produced by the planet's own temperature rather than bounced off it. That makes it far easier to study than most worlds, because astronomers can measure the planet's own output directly rather than trying to separate a faint reflection from an overwhelming star. There is a piece of physics here that connects the planet directly to the Sun. One of the main things controlling how light moves through Kelt 9b's atmosphere is the negative hydrogen ion, an ordinary hydrogen atom that has picked up an extra electron. It is a fragile, short-lived arrangement, and it is very good at absorbing light across a broad range of wavelengths. It is also the substance that governs the visible surface of the Sun. The same obscure ion that determines what our own star looks like is at work in the atmosphere of a planet, which is not a sentence that applies anywhere else. The star's color matters too. Because Kelt 9 is so hot, most of its output is not visible light at all. It is ultraviolet. And ultraviolet is precisely the part of the spectrum most efficient at severing chemical bonds and stripping atmospheres. The planet is not merely close to a bright star. It is close to a star whose light is specifically well suited to taking it apart. The atmosphere contains things that ought not to be gaseous at all. Iron has been detected there, in atomic vapor form. So has titanium. On any ordinary world, those elements are locked up in rock and metal, and it takes a furnace to get them to flow, let alone to float. Here they are simply part of the air. They are also leaving. Ultraviolet measurements have found magnesium and iron escaping the planet entirely, streaming outward into space. The planet is continuously losing an extended envelope of hydrogen, which reaches out well beyond the planet's own radius, a structure more like a comet's tail than anything a gas giant is supposed to have. The orbit is strange too. Kelt 9b does not circle its star's equator. Its path is nearly polar, carrying it almost over the star's poles. And the star itself is spinning fast enough to be visibly flattened, bulging at the equator and hotter at the poles. Because of that flattening, the planet experiences something like seasons. As it travels across the star's oblate face, the amount of radiation reaching it changes through the orbit. It is hotter when it passes over a pole and cooler when it crosses the equator. A near-polar orbit is also a piece of history. Planets form in flat disks around their stars' equators. This one is not there. Something tilted it, a gravitational encounter, a a companion star, some dynamical event in the system's past, and moved it into an orbit at an angle to everything else. The most sobering detail is the timeline. A-type stars are bright and short-lived. They burn through their fuel in a few 100 million years, against roughly 10 billion for the Sun. Within that window, Kelt 9 will begin to expand, and when it does, a planet already orbiting at about 3% of the Earth-Sun distance has nowhere to go. So this is not a stable arrangement that has been running for eons and will run for eons more. It is a world in the last stretch of a short life, in an orbit it did not form in, losing its own atmosphere in a visible stream, being evaporated in real time by a star that will finish the job well before it is done. We have just been somewhere hotter than most stars in the galaxy. The next entry on this list is the coldest place that has ever been measured, and it is colder than the universe is supposed to allow. Number 17, the place colder than empty space. There is a floor temperature to the universe, and almost nobody thinks about it. Empty space is not at absolute zero. It cannot be. The whole of space is filled with the cosmic microwave background, the cooled remnant of the radiation from the hot early universe, still traveling, still arriving from every direction. It has been expanding and cooling for nearly 14 billion years, and it is now down to about 2.725 Kelvin. But it is still there, and it still carries energy, and anything sitting in it absorbs that energy. Which means 2.725 Kelvin is the temperature you get for free. Put an object in the deepest emptiness between the galaxies, shield it from every star, wait as long as you like, and it will settle at the temperature of the background and stop there. To go lower, an object cannot simply stop producing heat. It has to actively pump heat out, faster than the background pours it back in. That is a machine's job. In a laboratory, going below the background requires pumps, shielding, refrigeration stages, and a continuous supply of power. Physicists routinely reach temperatures far lower, billionths of a degree, in atom-trapping experiments. But every one of those setups is an apparatus that somebody built and somebody maintains. About 5,000 light-years away, in the constellation Centaurus, there is a cloud of gas doing it unattended at a scale of a light-year, and it has been doing it for about 1,500 years. The Boomerang Nebula sits at roughly 1 Kelvin. It is the coldest naturally occurring place ever measured, and it is colder than the sky it hangs in. 1 Kelvin is minus 272 degrees Celsius. It is colder than the surface of Pluto by a factor of more than 30. It is colder than anything else known that nobody built. The name arrived first, and it was a mistake of a kind. In 1980, Keith Taylor and Mike Scarrett observed the object with the Anglo-Australian telescope, saw a faint lopsided shape, thought it resembled a boomerang, and the name stuck. Nothing about the name has anything to do with why the object matters. The temperature came 15 years later. Raghvendra Sahai at NASA's Jet Propulsion Laboratory and Lars Åke Neumann of the European Southern Observatory measured it using the Swedish ESO sub-millimeter telescope in Chile in observations taken between August and October of 1995. What they found was a signature that is impossible to argue with. They were looking at carbon monoxide gas, which is the standard tracer astronomers use for cold material, because it radiates efficiently even at very low temperatures. And the carbon monoxide in the Boomerang Nebula was not radiating against the cosmic microwave background. It was absorbing it. That only happens one way. A gas warmer than the background emits against it and shows up bright. A gas colder than the background absorbs it and shows up as a shadow. The boomerang appears as a shadow on the afterglow of the Big Bang, which is a direct measurement, not an inference. The mechanism turns out to be something in every kitchen. When a gas expands rapidly, it cools. That is the entire principle of refrigeration. Compress a gas, let it expand, and the expansion takes heat with it. The boomerang's central star, a dying star on its way to becoming a white dwarf, is shedding its outer layers at about 164 kilometers per second. The gas is expanding so violently that it drops its own temperature below the ambient floor of the universe and stays there. But that speed is the real puzzle, because it is roughly 10 times faster than a star of that kind should be capable of managing on its own. Ordinary dying stars shed their envelopes steadily, over long periods, at modest speeds. This one is throwing itself apart. The explanation that fits comes from later observations with the Atacama Large Millimeter Array, published by Sahai and colleagues in 2017. The picture they assembled is that this was not one star. A smaller companion star spiraled inward through the red giant's outer layers and was swallowed. The energy released by that plunge, a whole star falling through another star's envelope, is what drove the ejection at 10 times the normal rate. The star has lost more than a solar mass of material this way. Most of its own body has been thrown outward. The coldest place in the universe is the exhaust of a stellar collision. Stand inside it for a moment, if the phrase can be stretched that far. There is no wind, in any sense that would register. The gas is thin, far thinner than the best vacuum any laboratory can produce, and it is moving outward at 164 kilometers per second, but it is all moving together, so there is nothing to push against anything else. It is silent, and it is 1 degree above absolute zero, and it is dark. The star that produced all of it is somewhere behind, reduced to a diffuse point, wrapped in a dusty disk seen almost exactly edge-on, which crosses the nebula as a dark band and blocks most of the light that would otherwise escape. Everything is expanding away from everything else. And every second, the gas gets a little thinner and a little colder, because that is what expansion does, and there is no mechanism here doing any work. No pump, no power supply, no design. Just a star that flew apart hard enough to outrun its own heat. The central star deserves its own moment because of what it is in the middle of doing. It is what astronomers call a pre-planetary nebular object, and that is one of the shortest-lived stages in stellar evolution. A star at this point has finished being a red giant and has not yet become a true planetary nebula. It has thrown off its envelope, and the exposed core is heating up, but it is not yet hot enough to ionize the gas around it and make it glow the way a planetary nebula does. That transition takes a few thousand years against a stellar lifetime of billions. Catching a star in it is like photographing a specific afternoon in a person's life at random. The scale of what has been ejected is worth stating plainly. Sahai's team estimated a mass loss rate around 100 times higher than is typical for objects of this class, and a total ejected mass exceeding that of the Sun. The outer edge of the outflow has already traveled about 1/5 of a light-year from the star. A star has essentially disassembled itself and pushed the pieces outward across a distance that light takes 10 weeks to cross, and every part of that expanding shell is colder than the sky it is expanding into. The ALMA observations also corrected the picture in another way. Through optical telescopes, the object looks like 2 lobes joined at a waist, an hourglass, a bow tie. In millimeter wavelengths, where the cold gas actually radiates, the structure is far broader and rounder. It is close to a sphere. The hourglass is only the part that starlight manages to escape through, and the shape everybody had been looking at for decades was an artifact of where the dust happened to be thin. The cold is temporary. As the gas keeps expanding, it thins out, and thin gas cannot shield itself. The cosmic microwave background will win, eventually, and warm the cloud back up to the universal floor. Estimates put the window at centuries to a few thousand years, which, against the age of the star or the age of the universe, is nothing at all. which means the coldest place ever found is also a phase. It was not like this before, and it will not be like this for long, and the only reason anyone knows it exists is that a sub-millimeter telescope in Chile happened to look at it during the window. That nebula is cold because a star threw itself apart. The next object is what is left when a star has everything taken from it instead. Number 16. The planet that used to be a star. In 2009, a survey looking for millisecond pulsars picked up a signal with the Parkes radio telescope in New South Wales. Follow-up came from the Lovell telescope in the United Kingdom and the Keck telescope in Hawaii. The object was catalogued as PSRJ 1719, and it sits about 4,000 light-years away in the constellation Serpens Cauda. It is a neutron star. About 19 kilometers across, the width of a city, carrying roughly 1.5 times the mass of the Sun, and it is spinning more than 10,000 times a minute. That rotation is the useful part. A millisecond pulsar is one of the most precise natural clocks in existence. It sweeps a beam past the Earth with every rotation, and the pulses arrive with a regularity that can be measured to within fractions of a microsecond over years. Which means that if anything is orbiting the pulsar, the timing gives it away. As the pulsar is tugged toward and away from us, the pulses arrive slightly early and slightly late, in a repeating pattern, and the pattern describes the orbit. The timing of PSRJ 1719 showed a companion with an orbital period of 2 hours and 10 minutes. In August of 2011, Matthew Bales of Swinburne University of Technology in Melbourne and his colleagues published what that companion had to be, and the reasoning is worth following because the conclusion is forced rather than chosen. Start with the orbit. 2 hours and 10 minutes is extraordinarily short. The two objects are separated by about 600,000 kilometers, 1.5 times the distance from the Earth to the Moon, but with a neutron star at one end. The entire system would fit comfortably inside the volume of the Sun. Then take the mass. The timing gives a companion mass close to that of Jupiter. Now put those together. An object with Jupiter's mass, that close to a neutron star, experiences enormous tidal forces. If it were as diffuse as Jupiter, it would already have been pulled apart and spread into a disk. For it to hold together at that distance, it has to be far denser than Jupiter, denser than any planet that formed the ordinary way could possibly be. The measurements point to a density above 23 grams per cubic centimeter, more than 20 times the density of water, and well beyond anything in the solar system. There is only one kind of object that fits, and it is not a planet in any conventional sense. It is the exposed core of a white dwarf that has been stripped down to almost nothing. Which means this body began as a star. It burned hydrogen. It exhausted it. It became a white dwarf, the ordinary end state for most stars. And then it spent an enormous stretch of time in orbit around the neutron star, feeding it. Material spiraled off the white dwarf's outer layers and fell onto the neutron star, and every gram that arrived carried angular momentum with it. That transfer is what spun the neutron star up to 10,000 rotations a minute. This is a standard process. It is how millisecond pulsars are made, and it means that the fastest spinning neutron stars are also the oldest, which inverts the intuition most people bring to it. The white dwarf paid for that. It lost more than 99.9% of its original mass. Everything that could be taken from it was taken. What is left is the part that could not be taken, the degenerate carbon and oxygen core, compressed by its own gravity past the point where carbon can remain a disordered material. At those pressures, carbon crystallizes. So the object is, in the most defensible sense the phrase allows, a planet-sized crystal of carbon. It should be said clearly what that does and does not mean. This is not a diamond in the jeweler's sense. The crystal structure at those pressures is not the lattice of a gemstone, and the object is not transparent, not faceted, and not something anyone would recognize as a jewel. But the description that survives scrutiny is still remarkable. It is a body around 60,000 kilometers across, about 5 times the diameter of the Earth, made of crystallized carbon, that used to be a star and is now classified as a planet. Optical observations with the Keck telescope found nothing. No light from the companion at all. That absence was itself important evidence. Any ordinary star, or any object that had not been compressed into a degenerate state, would have shown up. It is worth putting a number on the pulsar's spin, because 10,000 rotations a minute is easy to read past. The period is 5.7 milliseconds. That means the neutron star turns on its axis about 175 times every second. An object with more mass than the Sun, packed into a sphere the size of a city, completing a full rotation in less time than a hummingbird's wing beat. The surface at the equator is moving at a significant fraction of the speed of light. And it is doing that because of material it took from the object now orbiting it. The system is also very old. 2 bodies that tightly bound, orbiting that fast, have been locked together for something on the order of 1 billion years. The orbit has had time to circularize almost perfectly. Whatever violence there was in the feeding phase is long over. What remains is a settled, quiet, permanent arrangement between a stolen core and the thing that stole from it. The discovery came out of a systematic effort called the High Time Resolution Universe Survey, which was designed to find exactly this kind of object by sampling the sky fast enough to catch pulsars spinning in milliseconds rather than seconds. It has since turned up dozens of new millisecond pulsars. This one was the strangest thing in the hall. There is a definitional problem here that has never been properly settled. Is this a planet? It has a planet's mass. It orbits a stellar remnant. By the working definitions, it qualifies. But it did not form as a planet. It formed as a star, and it was demoted by theft. There is no category for that, and the object quietly poses the question of whether a planet is defined by what it is or by how it got there. It also belongs to a family. There is a class of millisecond pulsars nicknamed Black Widows and Redbacks, and they are called that for a reason. They are actively destroying their companions, using radiation and particle winds to ablate them, grinding stellar objects down toward planetary masses over hundreds of millions of years. Astronomers have watched companions in that class at various stages of being consumed. This object is what the far end of that process looks like. A companion reduced past the point where it can be called a star at all, still bound, still going around every 2 hours and 10 minutes, with essentially nothing further to give. And it is still there. That is the part worth sitting with. Everything that made it a star, the fusion, the light, whatever planets it may have carried, the entire outer body of it, is gone, transferred across 600,000 kilometers of space, and used to spin up the thing that took it. The dead are not finished, though. The core remains, crystallized, orbiting the object that dismantled it, and it will keep doing so for far longer than it ever spent as a star. A dead star reduced to a crystal, still going around. The next 2 dead stars are going around each other, and they are doing it in the time it takes to make a cup of tea. Number 15. The year that lasts 5 minutes. In 1999, the German X-ray satellite Rosat recorded a source in the constellation Cancer that flickered with a period of 321.5 seconds. It was catalogued as RxJ0806 and later given the variable star name HM Cancri. The flicker was clean and strong and completely regular, and it did not obviously fit anything. 321.5 seconds is 5.4 minutes. The question that occupied the following decade was what that period actually represented. If it was the rotation of a single object, then this was simply a fast spinner, interesting but not extraordinary. If it was an orbit, then two objects were circling one another once every 5.4 minutes, and that would make HM Cancri the shortest period binary star system known by a wide margin. The argument ran from 1999 to 2010. It was settled by a team led by Heiss Roelofs, using the Keck telescope in Hawaii to take spectra of the system. Spectra show motion directly. As an object moves toward you, its light shifts slightly bluer, and as it moves away, it shifts redder. What Keck recorded was the unmistakable signature of two objects swinging around a common center. Two white dwarfs, the burnt-out cores of stars like the Sun, orbiting each other once every 5.4 minutes. The numbers that follow from that are difficult to hold in the mind, so let us take them one at a time. The two stars are separated by roughly 80,000 kilometers. That is about a fifth of the distance from the Earth to the Moon. Two entire stars, closer together than most of the space between us and our own satellite. They are each moving at more than 400 kilometers per second. For comparison, the Sun's orbit around the center of the galaxy proceeds at about 230 kilometers per second. These two objects are moving through their own orbit at nearly twice the speed our entire solar system moves through the galaxy. At 400 kilometers per second, each one crosses a distance equal to the diameter of the Earth in roughly 32 seconds. The system sits about 1,600 light-years away. Both stars together are smaller than the Sun. The entire structure, two stars and all the space between them, would fit inside the volume enclosed by a mid-sized planet's orbit, with a great deal of room to spare. And the period is not stable. That is the part that turns this from a curiosity into a laboratory. Any two masses orbiting each other radiate gravitational waves, ripples in the geometry of space-time itself, carrying energy outward. For most systems, the effect is unmeasurably small. The Earth's orbit around the Sun radiates gravitational waves at a rate that would take longer than the age of the universe to make any difference at all. But the strength of the emission scales enormously with how close and how fast the objects are, and HM Cancri is as close and as fast as anything known. So the energy is leaving. And energy leaving an orbit means the orbit shrinks. As it shrinks, the stars speed up, and as they speed up, they radiate harder, and the process accelerates. Precision X-ray timing with the Chandra Observatory measured the effect directly. The orbital period is getting shorter by about 1.2 milliseconds every year. That is a small number, but it is a measured number, and it is the direct fingerprint of gravitational waves carrying energy away from a system 1,600 light-years off. The orbit is visibly, measurably decaying on human timescales, and anyone can watch it happen simply by continuing to observe. It is worth explaining where the X-ray light itself comes from, because it is not the stars shining. White dwarfs are hot, but not hot enough to produce X-rays at this intensity. What produces them is a transfer. Material is being pulled off one white dwarf and is landing on the other, and it lands on a specific spot rather than spreading evenly, because magnetic fields channel it. That spot is heated to enormous temperatures by the impact. And as the receiving star rotates, the hot spot turns into view and out of view again, which is precisely the 5.4-minute modulation that Rosat recorded in 1999. The system is locked, so the rotation and the orbit keep the same time. What the satellite saw was a wound rotating past. Because of that, HM Cancri has an assigned role in the future of astronomy. LISA, the space-based gravitational wave observatory planned for the 2030s, will listen to a completely different part of the spectrum from ground-based detectors. Where those instruments catch the final fraction of a second of a black hole merger, LISA will hear the steady, continuous hum of compact binaries throughout the galaxy. Cancri is one of the loudest sources it expects to find, and it functions as a verification source. Its signal is already known well enough from other measurements that if LISA does not hear it, something is wrong with LISA rather than with the star. There is a useful distinction buried in that role. The gravitational wave signal from Cancri is not a burst. It is continuous. Black hole mergers produce a chirp, a rising tone that lasts a fraction of a second and then stops forever. This system produces a steady note at a fixed frequency, and it has been producing it for a very long time and will keep producing it for millions of years more. It is not an event. It is a sustained sound, and the whole galaxy is full of similar notes at slightly different pitches, waiting for an instrument capable of hearing them. The ending is not in doubt, only its form. Within a few million years, the two white dwarfs will touch. If mass transfer between them stabilizes, the pair may settle into a longer-lived arrangement and survive as a strange, tightly coupled object. If it does not stabilize, they merge. And a merger of two carbon-oxygen white dwarfs that pushes the combined mass past a critical threshold is one of the leading routes to a thermonuclear supernova. There is one more thing about this system that makes it belong on this list, and it concerns how it came to exist at all. Two stars cannot form 80,000 kilometers apart. There is no room. A star is born from a collapsing cloud that is enormously larger than the star it produces, and two forming stars that close would simply be one star. So this pair began far apart, as two normal stars, separated by something like the distance across a solar system. What brought them together is a process called common envelope evolution. As each star aged and expanded into a giant, it engulfed its partner. The companion, now orbiting inside a stellar atmosphere, experienced drag, and drag stole orbital energy, and the orbit shrank. The energy went into heating and ejecting the envelope. The pair spiraled inward while blowing away the material that was slowing them, and when the dust cleared, two stripped cores were left far closer than they started. They went through that more than once. Everything that made them stars, the hydrogen, the helium, the outer layers, the light, had to be shed before they could get this close. Cancri shows no hydrogen in its spectrum at all, because there is none left anywhere in the system. It belongs to a class called the AM Canum Venaticorum stars, which transfer helium rather than hydrogen for exactly that reason. So the 5-minute orbit is not the strange part. The 5-minute orbit is the consequence. The strange part is that these two objects had to destroy nearly everything they were in order to arrive at it. Those two will eventually touch. The next dead star is doing something to its neighbor that nobody thought a white dwarf was capable of, and it was in the catalogs for 45 years before anyone noticed. Number 14. The dead star that whips its neighbor. There is a star in the constellation Scorpius, called AR Scorpii. It is about 400 light-years away, which by galactic standards is closer than most of the stars you can pick out on a clear night. It was catalogued as a variable star in 1971. Somebody noted that its brightness changed, assigned it a designation, filed it under a category of slow variables, and moved on. And there it sat, in the records, for 45 years. Sky surveys came and went. Digital detectors replaced photographic plates. Whole generations of instruments were built and retired. Nobody had a reason to look at AR Scorpii again, because the catalogue already said what it was, and what the catalogue said was ordinary. In 2015, a small group of amateur astronomers pointed modest equipment at it. That is worth pausing on, because it is not a small thing. There is a community of people who observe known variable stars, not looking for anything in particular, simply watching objects that are already catalogued and recording what they do. It is patient, unglamorous work. And what these observers noticed was that AR Scorpii was not behaving the way its classification said it should. The brightness was not drifting over days. It was changing over minutes. They alerted professional astronomers. The follow-up was published in Nature in 2016 by Tom Marsh of the University of Warwick and his colleagues, and it described something that had never been observed before. The system contains two objects. One is a white dwarf, roughly the size of the Earth, carrying about 2/3 of the Sun's mass. The other is a cool red dwarf star, with about 1/3 of the Sun's mass. They orbit each other once every 3 hours and 36 minutes, which is fast but not remarkable. The white dwarf is also spinning on its own axis, and it completes a rotation once every 1.97 minutes. And as it spins, the entire system pulses. Not subtly, the brightness changes by roughly a factor of 4 every 1.97 minutes across the whole spectrum from ultraviolet through visible light and down into radio wavelengths. What is producing those pulses is the strange part, because the ordinary explanation does not apply. When a compact object in a binary system is bright, the usual reason is accretion. Material falls from the companion onto the compact object, forms a disk, heats up through friction, and radiates. It is the standard machinery of cataclysmic variables, and it has been studied for a century. AR Scorpii shows no evidence of that disk. There is no accretion structure doing the work. Instead, the white dwarf appears to be behaving like a pulsar, a rapidly rotating, strongly magnetized object flinging charged particles outward along its magnetic field and sweeping that outflow across its companion twice per rotation. The energy accounting closes on exactly that picture. The luminosity of the pulses exceeds the combined brightness of both stars. The light coming out is more than the two objects produce by their own heat and fusion. So it has to be coming from somewhere else, and it is. The white dwarf's rotation is slowing, measurably, and the energy lost from that spin down is enough to account for what is observed. The star is converting its own rotation into light and throwing it at its neighbor. The radio emission was the detail that made this genuinely new. Radio pulses from a binary of this kind had never been seen. The mechanism required is synchrotron radiation, electrons accelerated to speeds near the speed of light, spiraling in a magnetic field. That is the machinery of neutron star pulsars. A white dwarf is about 1,000 times larger than a neutron star, and its magnetic field is vastly weaker, and it was not thought capable of driving that process at all. Polarimetric measurements published the same year supported the interpretation directly. Polarization is the orientation of light waves, and strongly polarized light in a rotating pattern is the signature of a magnetic dipole doing work. The measurements showed exactly that. The white dwarf's magnetic field is estimated in the hundreds of megagauss. That is enormous by any laboratory standard. A strong hospital scanner runs around 30,000 Gauss, though it is around a millionth of what the most extreme neutron stars carry. The comparison to a neutron star pulsar is worth making concrete, because the difference in scale is the whole reason this was unexpected. A neutron star is about 20 kilometers across and can carry a magnetic field of 1 trillion Gauss or more. A white dwarf is roughly the size of the Earth, some 13,000 kilometers across, more than 600 times wider, and its field is a tiny fraction of that. Everything about the machinery that drives a pulsar depends on extreme compactness and extreme magnetism, and AR Scorpii has neither by those standards. It is running the same process with a fraction of the equipment, and it works. Then there is the red dwarf, which does not get a say in any of this. It is a real star, fusing hydrogen, going about its business, and it is being swept by a beam of relativistic particles every 59 seconds. Its atmosphere is being heated and stirred by the passage. It has presumably been on the receiving end of that for as long as the configuration has existed, which is likely a very long time. The astronomers describing the system use a technical term for what the white dwarf is doing. It is in the ejector state, meaning it is actively pushing material away rather than pulling it in, which is an accurate and rather bloodless way of describing a dead star, using the last of its rotation to lash the thing next to it. The pulse structure itself carries information. At some wavelengths, the system shows 2 peaks per rotation of the white dwarf, rather than 1, which is what you would expect if a beam is sweeping across the companion twice, once from each magnetic pole, or once as it approaches and once as it recedes. Long-term monitoring, drawing on data from the Kepler spacecraft's extended mission and from ground-based survey archives, has now tracked the system across years. The behavior is stable. This is not a transient episode that happened to be caught. It is what AR Scorpii does, continuously, and has been doing throughout the entire period it sat in the records marked as unremarkable. Since AR Scorpii, a second example has turned up. In 2021, a system was reported with a white dwarf spinning once every 25 seconds, doing something similar. A category that had exactly 1 member now has 2, which suggests these objects are not vanishingly rare. They are simply difficult to notice, because nothing about them looks unusual until somebody watches for 10 minutes with the right kind of attention. And that is the part of this entry that matters most for everything that follows. AR Scorpii is bright. It is 400 light-years away. It has been in the catalogue since 1971. The information that would have revealed what it was, that its brightness changes every 2 minutes, required no new technology, no space telescope, no survey. It required somebody to watch it for a few minutes and record what happened. For 45 years, nobody did. Not because it was hidden, and not because the instruments were inadequate, but because the entry in the catalogue said it was ordinary, and once something has been classified, the classification is what people see. That one was hiding in plain sight. The next entry cannot hide anywhere, because no instrument will ever reach it. It is a kilometer beneath the surface of an object nothing can approach. Number 13. The strongest material in the universe. Everything solid you have ever touched is mostly empty. An atom is a very small nucleus with electrons arranged at what is, proportionally, an enormous distance. If a nucleus were the size of a marble on the floor of a cathedral, the electrons would be somewhere near the walls. Almost all of the volume of any solid object is empty space held open by electrical repulsion. And that is where the strength of materials comes from. Steel is not strong because iron nuclei are hard to break. Steel is strong because when you push 2 iron atoms together, their electron clouds resist being overlapped. Every material property you have ever encountered, hardness, stiffness, the resistance of a table to your hand, is a negotiation between electron shells. The nuclei themselves are almost never involved. Inside a neutron star, that negotiation ends. Gravity at the surface of a neutron star is around 100 billion times what it is on Earth. Under that pressure, atoms cannot maintain their structure. Electrons are pressed into nuclei, combining with protons to make neutrons. And below a certain depth in the crust, the ordinary organization of matter simply cannot be sustained, and something else takes over. What takes over is one of the more unusual predictions in physics, and it was named in 1983, decades before anyone could calculate what it would actually be like. Here is the situation down there. 2 forces are competing at exactly the same scale. The strong nuclear force pulls protons and neutrons together into clumps. It is enormously powerful, but it only acts across tiny distances. Electrostatic repulsion pushes positively charged protons apart. It is weaker, but it reaches further. At ordinary densities, the strong force wins locally, and you get separate, well-defined nuclei with space between them. At the densities in a neutron star's inner crust, approaching the density of an atomic nucleus itself, the two are matched, and neither wins. So the matter compromises. It arranges itself into extended shapes. The names came from what the shapes looked like in the simulations. First, spherical clumps, gnocchi. Then, as you go deeper and the density rises, long cylinders, spaghetti. Then flat sheets, stacked like the pages of a book, lasagna. Then sheets with holes punched through them, Swiss cheese. Then tubes running through an otherwise solid background, bucatini or anti-spaghetti. Collectively, nuclear pasta. The naming is whimsical. The substance is not. In 2018, a collaboration involving Matthew Kaplan, then at McGill University in Montreal, working with Charles Horowitz at Indiana University and Andre Schneider at Caltech, set out to determine how strong this material actually is. They ran large-scale molecular dynamics simulations, modeling the individual particles and letting them interact. The computation took roughly 2 million processor hours. On a single good machine, that is about 250 years of continuous running. The answer they got is that nuclear pasta is approximately 10 billion times harder to break than steel. It may be the strongest material in the universe. Its shear modulus, the measure of how much it resists being deformed sideways, reaches around 10 to the 30th ergs per cubic centimeter. Its failure strain is above 0.1, which means it can be deformed by more than 10% of its own dimensions before it fails. For a material that's stiff, that is extraordinary. Engineering steel fails at strains hundreds of times smaller, because real steel is riddled with defects and cracks propagate from them. Nuclear pasta has no defects in that sense. It behaves closer to a perfect crystal. The density is what produces those numbers. A volume of neutron star crust, the size of a sugar cube, weighs on the order of 1 billion tons. There is no empty space left to compress. There are no electron clouds to push aside. There is nothing to give. Let us go down into it, since nothing ever will. Start at the surface. It is an iron lattice, and it is smooth, smoother than anything manufactured, because gravity 100 billion times Earth's flattens every irregularity. The temperature might be 1,000,000 degrees. Descend a few meters, and the atoms are already deformed, squeezed by pressure into shapes that are not spherical. Continue down. The electrons are stripped away entirely and move freely, and the nuclei become neutron-rich, holding numbers of neutrons that would be violently unstable anywhere else. Keep going. A few hundred meters down, the nuclei are so close together that the space between them is smaller than the nuclei themselves. And then the geometry begins. The spheres stretch into rods. The rods merge into sheets. The sheets stack, layer on layer, page on page, running for who knows how far. Then the sheets begin to open with holes, and then the solid and the empty change places, and you are inside a structure of tubes running through a continuous background. A kilometer down, you are in the strongest material that exists. And it is under so much stress, from the star's own rotation, from a magnetic field that can reach 1 trillion times Earth's, from the slow cooling and contraction of the whole object, that periodically it fails. Because it does fail. That is how any of this is known. Neutron stars occasionally show glitches, abrupt, tiny increases in their spin rate, detected in the timing of their pulses. The leading explanation involves the crust cracking and the superfluid interior transferring angular momentum outward. In magnetars, The crust can be fractured by magnetic stress, releasing energy in bursts that are detectable across the galaxy. The strongest material in the universe is being repeatedly torn apart by the object it belongs to. There is a second observable consequence, and it is more elegant. Because the crust is so strong, a neutron star can support genuine irregularities on its surface, mountains in the technical sense. And because the star is spinning, a mountain makes the star slightly asymmetric, and a spinning asymmetric mass radiates gravitational waves continuously. The maximum height of such a mountain is set by the crust's failure strain. With nuclear Pasteur's numbers, the ceiling comes out at somewhere around a few centimeters on a body 20 kilometers across. A few centimeters sounds absurd until you remember where it is. On a surface where gravity is 100 billion times Earth's, a centimeter is a mountain in every sense that matters, and gravitational wave observatories are already listening for exactly that signal. They have not heard it yet, and the non-detections themselves put limits on how tall the mountains can be, which puts limits on how strong the crust is. The Pasteur layer matters for one more reason, and it concerns where the crust ends. Beneath it, the star transitions into a uniform sea of neutrons, the core, whose properties remain one of the most sought-after unknowns in physics. The exact location of that boundary depends on how nuclear matter behaves at extreme density, which is precisely the question that neutron star measurements are designed to answer. Nuclear Pasteur sits directly on the frontier between what is understood and what is not. It also affects how the star cools. The odd geometry of sheets and tubes scatters electrons very effectively, which impedes the flow of heat outward from the interior. A neutron star wrapped in a layer of Pasteur cools differently from one that is not, and observations of young neutron stars losing heat over decades are one of the few ways to test whether the layer is there at all. And every neutron star has been through it. When a massive star's core collapses, it passes through these densities on the way down, in a fraction of a second, before the explosion happens. The same geometry that forms permanently in a crust forms briefly in the collapse itself. Every neutron star that exists was born through a moment of Pasteur. None of this can ever be sampled. The Pasteur layer sits perhaps a kilometer beneath the surface of an object whose surface cannot be approached at all. The gravity would flatten anything. The magnetic field would distort atoms into elongated shapes long before arrival. Nothing built of ordinary matter keeps its structure within 1,000 kilometers of the place. So the strongest substance in the universe is known entirely through simulation, through indirect inference, and through the fine timing of pulses that have been traveling for thousands of years to arrive at a radio dish and stutter very slightly. The strongest material in the universe is being cracked from within. The next object was slowed almost to a standstill by something even less likely, the part of itself it could not throw far enough away. Number 12. The star that was stopped by its own wreckage. In the constellation Norma, about 10,000 light-years away, there is an expanding shell of debris called RCW 103. It is a supernova remnant, the scattered remains of a massive star that exploded roughly 2,000 years ago. The shell is about 10 light-years across, and its expansion rate is how the age is known. At the center of it sits an X-ray source, catalogued as 1E161348. The designation begins with the numeral 1 and the letter E, because it was found by the Einstein Observatory, the first fully imaging X-ray telescope ever flown, in 1980. A supernova remnant with a compact object at its center is a familiar arrangement. The star exploded. Its core survived as a neutron star. The neutron star sits in the middle of the wreckage. The Crab Nebula has one, and it spins about 30 times a second. That speed is not an accident, and it is not optional. When the core of a massive star collapses, angular momentum is conserved. Take something roughly the size of the Earth and compress it to 20 kilometers, and whatever slow rotation it had becomes enormously fast. The same reason a spinning skater accelerates by pulling their arms in, except taken to an extreme that has no everyday analog. Newborn neutron stars are expected to spin with periods measured in milliseconds. Periods of seconds are ordinary for older ones. A period of minutes would already be exotic. 1E161348 has a period of 6.67 hours. 6 hours and 40 minutes. For an object with more mass than the Sun compressed into the size of a city, born 2,000 years ago from a collapse that should have left it spinning hundreds of times a second, the number was so far outside expectation that for a long time nobody believed it was a rotation. The leading interpretation was that it had to be an orbit. If the X-ray source were actually a binary, a neutron star with a small companion circling it every 6.67 hours, then the periodicity would make perfectly ordinary sense and the object would be unremarkable. That reading held for years, and it held despite the fact that no companion was ever detected. On the 22nd of June 2016, the object settled the argument itself. NASA's Swift satellite caught a bright, structured X-ray burst from the source. Short, hard, with the spectral shape and the timing characteristics that only one class of object produces. Magnetars, neutron stars carrying the strongest magnetic fields in the universe, announce themselves exactly this way, with sudden bursts driven by the rearrangement of their own fields. The burst confirmed it. This is a magnetar, and the 6.67 hours is a spin period. It is the slowest rotating isolated neutron star known, and it is not a close call. The next slowest are hundreds of times faster, which creates a timing problem that is genuinely difficult. The remnant is 2,000 years old, so the neutron star cannot be older than that. It was born spinning, almost certainly in milliseconds. And something slowed a city-sized object with the mass of a star from hundreds of rotations per second to one rotation every 6 2/3 hours in under 2,000 years. Ordinary magnetic braking cannot do that. Neutron stars do slow down. Every pulsar does, gradually, as it radiates and drives a particle wind. But the rates involved are nothing like this. Over 2,000 years, ordinary braking would barely register. To get from milliseconds to hours, you need to remove an amount of rotational energy comparable to a substantial fraction of a supernova, and you need to do it quickly. The explanation that survives requires the star's own debris. In a supernova, not all of the material ejected actually escapes. Some of it is thrown outward with less than the escape velocity, and it comes back down. If even a small quantity of that fallback material settled into a disk around the newborn neutron star, models suggest a mass on the order of a billionth of the Sun is sufficient. Then the star's enormous magnetic field would grip that disk. And a magnetic field anchored in a spinning star and threading a surrounding disk acts as a brake. The star drags the disk resists, angular momentum flows out of the star. With a dipole field around 5 × 10⁻⁵ Gauss, which is in the magnetar range, calculations show this can drag a millisecond spin down to a period of hours within 1 to 3,000 years, which matches the age of the remnant. So the picture is this. 2,000 years ago, a star died. The collapse of its core produced a neutron star spinning hundreds of times a second, with more rotational energy than almost anything in the universe. The explosion threw the star's outer body outward. Most of it escaped, and it is still expanding, and it is the shell we see. But a small fraction of it did not escape. It went up, slowed, and fell back. It settled into a ring around the object at the center. And it has spent 20 centuries applying a torque against the rotation that object was born with, until the spin was almost entirely gone. Nothing external did this. There was no companion, no collision, no interference from outside. The star was stopped by the part of itself that it could not throw far enough away. The material that failed to escape came back and spent 2,000 years breaking the corpse it came from. It is a closed loop, and there is something specifically bleak about it that a more violent story would not have. It is worth putting the magnetic field in context, because magnetar is a word that gets used without much sense of what it means. Earth's magnetic field, the one that turns a compass needle, is under a single Gauss. A refrigerator magnet is around 100. A powerful hospital scanner, the kind that requires an entire room of shielding and a warning sign on the door, reaches about 30,000 Gauss. A magnetar's field is around 10 to the 15th Gauss, which is 1,000 trillion. The gap between a hospital scanner and a magnetar is roughly the gap between a whisper and something that has no comparison in ordinary experience. At that field strength, atoms are deformed into elongated shapes, and ordinary chemistry cannot function. Fallback disks, meanwhile, have been proposed for decades as a general phenomenon around newborn neutron stars, and they have been extremely difficult to confirm. They should be faint, small, and short-lived. The object at the heart of RCW 103 is one of the strongest cases that they exist at all, and the evidence is not an image of a disk, but the fact that something has clearly been breaking this star for 2,000 years and nothing else fits. The object is not quiet, for what it is worth. It varies in X-ray brightness by large factors over years, entering active states and returning to quiescence, and it has shown at least 3 major outbursts across its observational history. And it opened a door. Since 1E161348, astronomers have found radio sources pulsing on timescales of minutes and tens of minutes, objects that should not be able to emit at all, because the standard mechanism that powers a radio pulsar is supposed to switch off when rotation gets too slow. This was the first object to establish that neutron stars can get much slower than anyone had allowed for, and still be doing something. That star was stopped by its own wreckage. The next ones stop on their own, for weeks at a time, and nobody knows what flips the switch. Number 11. The dead stars that switch themselves off. We are halfway down the list now, and it is worth taking one moment to look at what has already accumulated. We started with a rock that carries rings it should not be able to hold, and a planet sitting inside the volume its star used to occupy. We went to a world hotter than most stars in the galaxy, and then to a cloud colder than the universe's own floor temperature. We found a planet made of crystallized carbon that used to be a star, 2 dead stars completing an orbit in 5 minutes, a dead star whipping its neighbor with a beam every 2 minutes, and a substance 10 billion times harder to break than steel, buried under a surface nothing can approach. And we have just left a neutron star that was slowed almost to a standstill by the part of its own explosion that failed to escape. Every one of those is a confirmed object with a catalog entry. And every one of them was found in the past few decades, mostly by people who were looking at something else. The next entry continues a pattern that has been quietly building since number 14, the pattern of things that were in the records the whole time. A pulsar is a rotating neutron star that sweeps a beam of radio emission past the Earth, producing a pulse with every rotation. The defining property of a pulsar is reliability. The timing is precise enough to be used as a clock, to test general relativity, and to search for gravitational waves by watching for tiny correlated deviations across an array of them spread around the sky. Pulsars do not stop. PSRB 1931 plus 24 stops. It was identified as an intermittent pulsar in work led by Michael Kramer, published in 2006. The star rotates once every 0.8 seconds, and when it is on, it behaves like a completely ordinary pulsar. Then it switches off. the emission does not weaken. It vanishes below the detection threshold entirely, and it stays gone for somewhere between 25 and 35 days. Then it comes back, typically for 5 to 10 days, and the cycle repeats. It is on roughly 10% of the time. For 9 days out of every 10, one of the more thoroughly studied neutron stars in the galaxy is, as far as any instrument can tell, not there. The transitions are the first strange detail. They are abrupt. The switch happens in under 10 seconds. An object with the mass of the Sun compressed into the size of a city, spinning at a fixed rate that does not change, alters what it is fundamentally doing in less time than it takes to read this sentence. The second detail is the one that turned this from a curiosity into a genuine physics result. All pulsars slow down over time. Emitting radiation and driving a wind of charged particles costs angular momentum, and the star pays for it by rotating fractionally more slowly each year. The rate is measurable to extraordinary precision. When PSRB 1931 plus 24 is on, it slows down about 50% faster than when it is off. That single fact is a direct measurement of something that had previously been assumed rather than observed. It says the braking force on the star is being supplied by the outflowing charged particles in its magnetosphere. When the emission shuts off, the particle flow shuts off too, and the star coasts. Which means the switch is not simply a beam swinging out of our line of sight. The machinery that produces the beam is genuinely being turned off, and then genuinely turned back on. For the first time, a pulsar's magnetosphere became something that could be weighed rather than modeled. The object did not stay alone for long. In 2012, a team led by Fernando Camilo announced PSRJ 1841, a pulsar with a period of about 912 milliseconds, which switched off and stayed off for 580 days. More than a year and a half of complete silence, and then it resumed. Its spin-down rate in the on state is around 150% higher than in the off state, an even more extreme version of the same effect. A third object, PSRJ 1832, shows off states lasting hundreds of days. It is worth distinguishing this from something pulsars have long been known to do. Many pulsars null. They drop a pulse here and there, or a short run of them, and then carry on. Nulling has been studied since the 1970s, and it is understood as a normal, if unexplained, part of pulsar behavior. But nulling operates on the scale of individual rotations, a missed beat, or a few seconds of quiet. Intermittent pulsars are off for weeks, months, or years. The difference between the two is not a matter of degree. It is many orders of magnitude, and there is no obvious reason to think the same process is responsible. Nobody knows what flips the switch. The proposals include a global reconfiguration of the magnetosphere, changes in the supply of charged particles feeding the emission region, some kind of external trigger, and even the possibility that something is orbiting the star and periodically interfering with it. None of these is established, and the quasi-periodic but not quite regular timing of the cycles argues against the simplest versions of the orbiting object idea. Then, in 2025, the story turned. China's 500-meter aperture spherical telescope, FAST, the largest single-dish radio telescope in the world, with a collecting area equivalent to roughly 30 football pitches, was pointed at PSRB 1931 plus 24 during one of its off states. And it heard something. Not full pulses. Weak emission, containing occasional short bursts, at a level far below anything 20 years of monitoring with less sensitive instruments had been able to reach. The star was never entirely off. It had been whispering, below the threshold of every telescope that had looked at it, for 2 decades. There was more in the data. The pulse profile during the off state is measurably narrower than during the on state. That is not what a simple shutdown looks like. A narrower profile points to a real structural change in the magnetosphere, the emission region contracting, the plasma supply reorganizing, rather than a switch being thrown. There is a practical consequence to all of this that goes beyond these three objects. The sky is surveyed by taking snapshots. A telescope points at a patch, records for a while, and moves on. If a pulsar happens to be in an off state during the observation, it records as empty sky. PSRJ 1841 was silent for 580 consecutive days. If a survey had looked at it once, at any point during that window, the result would have been filed as nothing at all. There are around 3,000 known pulsars in the Milky Way, and the total population is estimated to be far larger, hundreds of thousands, most of them beaming away from us or too faint to reach our instruments. Those two categories were always understood. This is a third one, and it was not accounted for. Pulsars that were pointed at us, bright enough to detect, and simply not transmitting on the day somebody checked. Which means the census of pulsars in the galaxy may be significantly short. Not because those objects are faint, or distant, or obscured, but because the method used to count them assumes that a working star is always working. Those stars were silent, but still there. The next one is not silent, not still, and not staying. It is leaving the galaxy for good, and it is made of the wrong elements. Number 10, the shrapnel that survived, the explosion. There is a faint object about 2,000 light-years away, catalogued as LP4365, and also known by an older designation GD492. It was noticed decades ago, recorded and shelved. Nothing about it demanded attention. In 2017, work led by Stefan Venz at the Astronomical Institute of the Czech Academy of Sciences examined its spectrum properly and found that it did not look like anything it was supposed to be able to look like. The first problem was what was missing. There was no hydrogen. There was no helium. Those two elements make up roughly 99% of the ordinary matter in the universe. They dominate the atmosphere of essentially every star, including white dwarfs, which typically show one or the other and sometimes both. Finding a stellar object with neither is like finding a building made without brick, stone, wood, concrete or steel. Whatever it is made of, it is not made of the things that things are made of. What it had instead was oxygen and neon, with substantial quantities of magnesium, silicon, sulfur, and other heavier elements. That is not a stellar atmosphere. That is nuclear ash. Specifically, it is the signature of incomplete oxygen and silicon burning, the set of products you get partway through a thermonuclear detonation that did not run to completion. Those elements are what a star makes in the final seconds before it explodes, and they are supposed to be flying outward through space, not sitting on the surface of something. The second problem arrived a year later, and it was the motion. Gaia, the European spacecraft that has been measuring the positions and movements of more than 1 billion stars, provided the numbers in work published in 2018 by Roberto Radi and colleagues. LP4365 is moving at about 852 kilometers per second relative to the galaxy, with an uncertainty of only around 10 kilometers per second. That is above the escape velocity of the Milky Way. This object is not orbiting the galaxy. It is leaving it. Permanently. It will pass out through the halo and spend the remainder of its existence in intergalactic space, and nothing will bring it back. Run the trajectory backwards, and it comes from the galactic disk a few million years ago. Put the two problems together, and only one story fits. This object was part of a white dwarf that underwent a thermonuclear supernova, and it did not finish exploding. The mechanism has a name, a Type Yax supernova. In an ordinary Type 1a supernova, a white dwarf detonates and is completely destroyed. The entire star is converted and dispersed. Nothing survives, and astronomers have never found a remnant at the site of one. In a type Y-ax, the burning is asymmetric and incomplete. A deflagration front, a burning wave that travels below the speed of sound rather than above it, sweeps through part of the star, converts some of it to heavier elements, and fails to unbind the whole thing. The star is partially burnt, violently kicked, and left over. The speed came from being in a binary. The white dwarf had a close companion, and the two were orbiting each other at hundreds of kilometers per second, which is what stars do when they are that close together. When the explosion partly destroyed one of them and blew away most of the gravitational binding, both objects were released at whatever speed they happened to be traveling at that instant. Like a hammer thrower letting go. The companion went one way at enormous speed. This survivor went the other. So it is not a star in any conventional sense. It is a fragment of one. It is still glowing from residual heat rather than from fusion, and its surface is made of the residue of its own explosion. Its density is low for a white dwarf because the detonation puffed it up and it has not finished settling back down. It also spins slowly. Measurements published in 2021 found a rotation period of 8.9 hours, which is another oddity. An object that has been through that much violence ought to be spinning fast. The leading explanation is that the material ejected during the explosion carried angular momentum away with it. Go out and look at it, if the imagination will stretch that far. It is beyond the edge of the galactic disk now. Behind it, the whole structure of the Milky Way is visible as a receding object, the way a city looks from a plane, an organized thing, with a shape getting smaller. Ahead of it there is nothing for a very long time, and then more nothing after that. The object itself is small and dim, still slightly too warm, turning once every 9 hours or so. Its atmosphere is a thin layer of oxygen and neon, the ash of the event that made it. It is not decelerating because there is nothing out there to decelerate against. This is what it will be doing when the sun becomes a red giant, and it is what it will be doing long after that. The chemistry carries more information than simply being wrong. Manganese and chromium are present in the atmosphere, and the ratio between them is diagnostic. Those two elements are produced together in thermonuclear burning, but the proportions depend sensitively on the density at which the burning happened. The ratio measured here indicates burning at high density, which points to a white dwarf close to the critical mass at which such a star becomes unstable. That is not a vague inference. It is a reading of the conditions inside an explosion taken from the surface of the thing the explosion failed to destroy several million years later. There is also the question of where the explosion happened, and that is answerable. The reconstructed trajectory places the event somewhere in the galactic disk around 5 to 10 million years ago. On astronomical timescales, that is recent. It is recent enough that the supernova remnant itself, the expanding shell of material that did escape, may still be identifiable, which would give astronomers both halves of the same event, the debris in one place and the survivor in another, moving away from it at 850 kilometers per second. And it is not one of a kind. A survey published in 2019 found 3 more objects carrying the same fingerprint, oxygen and neon atmospheres, the same distinctive ashes in remarkably similar amounts, the same high velocities. There is now a recognized class, partly burnt runaway stellar remnants. 4 known survivors of explosions that were supposed to leave nothing behind at all. It is also the nearest unbound hyper-runaway star to the Sun, at roughly 630 parsecs. Of all the objects that have ever been flung out of this galaxy, this is the closest one anybody has managed to identify, which says less about the object than about how difficult they are to find. It is faint. It is small. Its only distinguishing feature is a spectrum that looks wrong, and a proper motion that only became measurable when a dedicated astrometry mission spent years watching the entire sky. There is a related population as well. Gaia has identified objects nicknamed D6 stars, moving at over 1,000 kilometers per second, which are thought to be the surviving companions rather than the exploded star itself, flung away when their partner detonated. The wreckage of these events comes in more than one form, and both forms are still in flight. Which means the accounting for thermonuclear supernovae has a category that nobody was counting. Type Y-axis explosions are estimated to make up a meaningful fraction of all thermonuclear supernovae, possibly a fifth to a third of them. If that is right, then bound remnants are not exotic. They are common. And since the galaxy has been producing them for its entire history, and every one of them leaves at escape velocity, intergalactic space should hold an accumulated population of these things, cooling slowly, invisible, drifting apart from each other forever. That fragment is the aftermath of an explosion that failed to finish. The next entry is the same failure, caught in the act, with photographs from before and after. Number 9. The star that survived its own supernova and came back brighter. In 2012, a supernova appeared in NGC 1309, a spiral galaxy about 110 million light-years away in the constellation Eridanus. It was catalogued as SN 2012Z. Its spectrum looked like a Type Ia supernova, the thermonuclear detonation of a white dwarf, but it was noticeably dimmer than a Type Ia should be, and the material it threw off was moving more slowly than expected. It was classified as a Type YX, the same peculiar variety we have just been discussing. And then something happened that almost never happens in astronomy. It turned out that the galaxy had already been photographed, repeatedly, in high resolution, for years. NGC 1309 was a distance ladder calibrator. It had hosted an ordinary Type Ia supernova in 2002, and because Type Ia supernovae are used as standard candles to measure cosmic distances, Hubble had imaged the galaxy carefully and often as part of the work of calibrating that scale. Which meant that when SN 2012Z went off, there were already sharp images of the exact patch of sky where it had happened, taken before it happened. Curtis McCulley, then a graduate student at Rutgers University, went through those pre-explosion images. He sharpened them, worked out precisely where the supernova had occurred, and found a source sitting at that position. The result, published in 2014, was the first time the progenitor system of a thermonuclear supernova had ever been identified in advance. Astronomers had photographs of the star before it exploded. The system appeared to consist of a white dwarf and a bright blue companion, most likely a helium-burning star that had been transferring material onto the white dwarf until it detonated. That alone would have earned the object a place in the textbooks. But the obvious next step was to wait for the supernova to fade and then look again. The expectation was straightforward. If the white dwarf had been destroyed, as thermonuclear supernovae destroy white dwarfs, then the site should be either empty or showing only whatever remained of the blue companion. Either way, it should be dimmer than the original system, because the star that made up most of the light was gone. In 2022, Macaulay and his colleagues, by then working at Las Cumbres Observatory and the University of California, Santa Barbara, published the follow-up. Hubble had imaged the position again, years after the explosion, once the supernova's own light had faded away. There was a source there, and it was not fainter than the pre-explosion system. It was brighter. The star had survived its own supernova, and it had come out of the experience more luminous than it went in. The mechanism, as it is now understood, is a partial detonation. The white dwarf ignited. Burning swept through part of it, converting material to heavier elements and throwing a substantial quantity of it outward at high speed. But the explosion was not energetic enough to overcome the star's own gravity everywhere. Some of the material was ejected and escaped. Some of it was thrown up and fell back. What was left is what astronomers call a bound remnant. And that remnant is not an ordinary white dwarf, which is why it is brighter rather than dimmer. The explosion deposited an enormous amount of energy into the material that stayed. The object puffed up, inflated into a hot, low-density, greatly enlarged state. A larger surface radiating at a high temperature emits far more light than a compact white dwarf does. So the star is brighter now not because it gained anything, but because it was blown up like a balloon and has not yet deflated. It will deflate. Over thousands to millions of years, the remnant will contract and cool, dimming as it goes, and eventually settle back into something dense and dark again, a white dwarf of a sort, with a surface enriched in the iron group elements its own explosion produced. Which is exactly the chemistry found on the surface of the object we looked at a moment ago, still traveling out of the galaxy at 850 kilometers per second. That is the connection worth holding on to. SN 2012. Z shows the process in the act, photographed before and after. The runaway fragment shows the aftermath, several million years on, cooled and settled and leaving. They are two frames from the same sequence, taken from opposite ends of it, and together they describe a kind of ending that nobody had a category for. The dead are not finished. That has been true for several entries now, but here it is more insistent than usual. This object did not merely persist after its death, the way a stripped core persists in orbit. It underwent the event that is supposed to be definitionally final, and then it kept going, and for a while it is doing more than it did before. It is worth dwelling on how unlikely the observational setup was, because it will not be repeated often. To catch a supernova progenitor in advance, three things must coincide. The galaxy has to be close enough for a telescope to resolve individual stars in it. It has to have been imaged deeply and repeatedly before the explosion, for reasons unrelated to the explosion. And the supernova has to occur in a part of the galaxy that was actually covered by those images at sufficient depth. Supernovae are not announced ahead of time. There is no way to arrange the photographs. For SN 2012Z, all three happened to be true, and they were true because of an entirely different research program carried out years earlier for entirely different reasons. The astronomers who took those Hubble images of NGC 1309 were measuring cosmic distances. They had no idea they were photographing a star that would explode, survive, and settle a decades-old question about what thermonuclear supernovae actually do. The blue companion in those images is its own piece of the story. Its color and brightness point to a helium-burning star, which means the material being fed to the white dwarf was helium rather than hydrogen. That matters because helium accretion produces a different kind of ignition. It can detonate a surface layer, which sends a shock inward, which can trigger burning in the core. That route to explosion is one of the leading models for how these partial detonations happen, and here it was photographed rather than inferred. The wider significance concerns something that reaches well beyond one galaxy. Type Ia supernovae are the standard candles that revealed the accelerating expansion of the universe. Their entire value as a measuring tool rests on uniformity, on the assumption that a white dwarf reaching a critical mass explodes in essentially the same way every time, with essentially the same brightness, and is completely destroyed in the process. If you know how bright the explosion was, and you measure how bright it appears, you know how far away it is. That logic underwrites a great deal of modern cosmology. Type Yax explosions are the counterexample sitting next to it. Same class of star. Related trigger. Fundamentally different outcome, with something left behind. Between 30 and 50 of them are now known, and they may account for a substantial fraction of all thermonuclear supernovae in the local universe. Other Type Y-axis events have been searched for surviving remnants, and a small number of candidates have been examined. None is as clean as this one, for the same reason that made this one possible: the before and after images. Most supernovae occur in galaxies nobody happened to be photographing. Work on SN 2012 Z has continued. Follow-up analysis reported in 2025 reinforced that the surviving object is real and is behaving the way the bound remnant model predicts. So the star that exploded in 2012 is still there. It is still bright. It is slowly on its way back to being a white dwarf again, and it will get there in due course, and by then, the light from all of this will have been traveling for a very long time. A star that survived its own supernova is at least still a star. The next object on this list is a star with something else living inside it, and it was predicted 50 years ago and has never been confirmed. Number 8. The star with a dead star for a heart. In 1975, Kip Thorne at Caltech and Anna Zitkoff, who was then his graduate student, worked out what would happen if a neutron star ended up inside another star. The setup is not exotic. Massive stars are usually born in pairs. The heavier of the two evolves faster, exhausts its fuel first, and explodes, leaving a neutron star behind. If the system stays bound, and many do, you have a neutron star orbiting an ordinary star. Then time passes. The surviving star runs out of hydrogen in its own core and swells into a red supergiant, expanding to hundreds of times its original size. And if the orbit is close enough, or if the supernova's kick nudged the neutron star inward, the neutron star ends up inside the supergiant's outer envelope. Once that happens, the outcome is not in doubt. Drag inside the envelope steals orbital energy. The neutron star spirals downward through the star it was orbiting, losing altitude with every pass until it reaches the center. What you have then is a single object with two histories. From outside, it is a red supergiant. Enormous, cool, red, and, this is the important part, essentially indistinguishable at a glance from any other red supergiant. It would sit in a catalogue looking entirely normal. Inside, where an ordinary supergiant has a core of fusing gas, there is a neutron star. 20 kilometers across, more massive than the Sun, with a surface gravity 100 billion times the Earth's. The physics that follows has no analogue anywhere else in the universe. An ordinary star shines because fusion in its core releases energy, and the outward pressure of that energy holds the star up against its own weight. A Thorne-Zitkoff object does not work that way. Its energy comes from material falling onto the neutron star's surface, where it is compressed to conditions no stellar core ever reaches. In the more massive versions, the star's convective envelope reaches almost all the way down to the neutron star, which means material is carried into that extreme region, transformed, and carried back out toward the surface. And the nuclear reactions in that region run in an unfamiliar direction. In an ordinary red giant, heavy elements are built by slow neutron capture, nuclei absorbing neutrons one at a time over long periods, with time to decay in between. In the environment around a buried neutron star, the conditions instead favor rapid proton capture, sometimes called the ERP process. Different reactions, different products, a different set of elements. The theory predicts two distinct kinds. The low-mass version is supported by degenerate pressure and is relatively short-lived. The high-mass version is convective throughout and can persist for something on the order of 100,000 to 1,000,000 years, long by human standards, brief against the lifetime of a star, which is part of why finding one is difficult. Neither kind lasts indefinitely, and the ending is worth stating. The neutron star at the center is gradually accreting the envelope around it. It grows. And a neutron star can only grow so far before it exceeds the maximum mass that neutron degeneracy pressure can support, at which point it collapses into a black hole. So the eventual fate of one of these objects is a black hole forming inside a living star, which then consumes the star from the middle outward. The scale involved is what makes the concealment possible. A red supergiant is enormous. Place a typical one where the Sun is, and its surface would reach past the orbit of Jupiter. Against something that large, a neutron star 20 kilometers across is a speck. There is no external sign. The star's size, color, and temperature are set by its envelope, and the envelope does not care very much what is heating it from below. So Thorne and Zitkov's successors worked out what that would look like from outside. The prediction was specific: excess molybdenum, excess rubidium, excess lithium, excess calcium, in ratios that ordinary stellar nucleosynthesis cannot produce. And because the envelope is convective, those elements would be carried up to the surface, where a spectrograph could see them, which turned the search into a chemistry problem. Find a red supergiant with the wrong elements in its atmosphere, and you have found a star with a corpse at its center. In 2014, Emily Levesque, then at the University of Colorado, and her collaborators reported that a star called HV 2112, a red supergiant in the Small Magellanic Cloud, about 200,000 light-years away, showed exactly those anomalies. Enhanced rubidium, enhanced molybdenum, enhanced lithium, possibly calcium and potassium as well, all measured relative to other supergiants in the same galaxy, so the comparison was fair. It was announced as the first candidate Thorne-Zitkov object, 40 years after the prediction. It has not held cleanly, and the honest account of what happened next is a good illustration of how these things actually go. In 2016, an analysis of the star's motion across the sky suggested it might not be in the Small Magellanic Cloud at all, that it might be a much closer star in our own galaxy, seen in the same direction, in which case it would be far less luminous and would not be a supergiant. That would have ended the candidacy. Then in 2018, data from Gaia settled the distance question and put it back in the Small Magellanic Cloud. It is a supergiant, after all. But in the same year, a critical re-evaluation argued that the abundance pattern is also consistent with a super-asymptotic giant branch star, a very massive but otherwise entirely ordinary dying star, which can produce broadly similar chemistry through conventional processes, with no neutron star involved anywhere. Other candidates have been proposed over the years: HV 11417, U Aquarii, VX Sagittarii. None of them is settled either. So here is the honest status, 50 years after the prediction was made. The objects should exist. The formation channel is plausible and well studied, and population modeling published in 2025 suggests a meaningful number of them in the galaxy, including formation routes through common envelope evolution that had not previously been explored. Theoretical work has also examined what happens when one of them dies, on the reasonable assumption that the ending should not look like a normal supernova. But no unambiguous example has been confirmed. And the reason is built directly into the problem. A Thorne-Zitkov object is predicted to look almost exactly like a red supergiant, and the galaxy contains a great many red supergiants. There is also a scientific value here beyond the strangeness, and it is worth naming. The ERP process operates at temperatures and densities that laboratory nuclear physics can only approach indirectly. Particle accelerators can produce some of the relevant reactions one at a time, under carefully constructed conditions, but nothing on Earth can sustain that environment. A Thorne-Zitkov object would be a natural experiment running continuously for 100,000 years, and reading its surface chemistry would be a way of measuring nuclear physics that is otherwise inaccessible. That is a substantial part of why the search has continued for half a century, despite producing no confirmations. The other loose end is what these objects look like when they end. If the death of a Thorne-Zitkoff object does not resemble a standard supernova, and there is good reason to think it would not, then it is possible that some of the unusual transients already sitting in survey archives, filed as peculiar explosions of uncertain type, are these objects finishing. Nobody has matched one yet, but nobody had a template to match against until recently. New approaches are being attempted. Work published in 2025 proposed identifying them through neutrinos, on the grounds that the interior processes should produce a neutrino signature that ordinary stellar fusion does not, which would be a way of seeing past the envelope rather than trying to read chemistry off the surface. Which leaves the possibility that has to be stated plainly, because it is the entire reason this object sits at number 8. Betelgeuse is a red supergiant. So is Antares. There are hundreds of them catalogued, and several are bright enough to find with the naked eye on any clear night, without equipment, without effort. If Thorne-Zitkoff objects exist at anything like the rates the models suggest, then some small number of the red supergiants visible from Earth have a neutron star at the center. They are not doing anything to announce it. They look correct. The chemistry that would reveal them requires a high-resolution spectrum and a careful comparison against other stars of the same type, and even then, the answer comes back contested. You can walk outside tonight, find a red supergiant, and have no way of knowing whether you are looking at a star or at something wearing one. We cannot tell which supergiants are hiding a corpse. The next object hid nothing. It simply happened to be pointed at us, and that is the only reason anyone has ever seen one. Number 7. The collision caught halfway through. In 2004, NASA's Galaxy Evolution Explorer, an ultraviolet survey satellite, usually called GALEX, recorded something around a star catalogued as TYC 2597, roughly 6,000 light-years away in the constellation Hercules. It was a ring. Large, faint, and very nearly a perfect circle. Everything about it was wrong from the beginning. It was bright in ultraviolet and essentially absent in visible light. That is unusual on its own. Most nebulae glow across a range of wavelengths, and something that shows up in one narrow band and nowhere else is a signal that an unusual process is at work. Its shape was almost perfectly round, which nature does not often manage at that scale. And the star at the center appeared to be an ordinary evolved star with a dusty disk around it. Ordinary evolved stars with dusty disks do not produce enormous ultraviolet rings. Mark Seibert and Christopher Martin, who were part of the GALEX team, took the object seriously and could not place it. What followed was 16 years of work. They gathered data from Hubble, from Keck, from Palomar, from the Wide-Field Infrared Survey Explorer, from ground-based spectrographs. Each new dataset added constraints, and each new constraint eliminated candidate explanations. It was not a planetary nebula, the shell of gas thrown off by a dying star, because the central star was the wrong kind and the emission was the wrong kind. It was not a supernova remnant. The energetics did not work, and there was no evidence of the shock structure. It was not a debris disk, or a shock front from a stellar wind, or a light echo bouncing off surrounding material. Every candidate failed on some measurement. The object sat unexplained for 16 years in the archives of a mission that had launched, operated, and been retired in the meantime. The answer arrived in November of 2020 in a paper led by Kerry Hoadley, then at Caltech, working with Martin and a team that included several of the original GALEX researchers. Their model is elegant, and once stated, it is obvious in retrospect. The ring is not a ring. It is the base of a cone. A few thousand years ago, TYC 2597, a star broadly like the Sun, engulfed and merged with a smaller companion. The merger threw material outward in two opposite directions along the axis of the collision. Two cones of debris expanding away from each other. And from Earth, one of those cones points almost directly toward us, and the other almost directly away. When you look down the axis of an expanding cone, you see a circle. The rim of the cone is where your line of sight passes through the most material, so the edges appear bright and the middle appears empty. The perfect circularity that had made the object so puzzling was not a property of the object at all. It was a coincidence of viewing angle. The ultraviolet glow has an explanation too, and it is the reason nobody found this with an ordinary telescope. The debris is plowing into the interstellar material around the star. That collision excites molecular hydrogen, and excited molecular hydrogen fluoresces in the far ultraviolet and produces almost nothing in visible light. So the object was effectively invisible to every instrument that was not looking specifically in the ultraviolet, which is a narrow category. Galax itself deserves a mention here, because the object is a product of the mission's particular blind spot and particular strength. It operated from 2003 to 2013 and surveyed the entire sky in ultraviolet, a part of the spectrum that Earth's atmosphere blocks completely, which means it can only be observed from space and had never been mapped comprehensively before. A whole sky survey in a band nobody had systematically looked at was always going to turn up things without precedent. The Blue Ring Nebula was among the most puzzling of them, and it outlasted the mission that found it by 7 years. The angular size is part of why it drew attention. The ring is large enough on the sky to be well resolved, rather than appearing as a smudge, which meant its circularity was obvious and precisely measurable. Had it been smaller, the shape would have been ambiguous and it might never have been flagged. The very property that made it so hard to explain, that impossible roundness, is the reason anybody bothered trying. What makes the Blue Ring Nebula scientifically valuable is not its strangeness. It is its timing. Stellar mergers are not rare. A large fraction of stars are in binary systems, and mergers are a normal outcome for a certain proportion of them. Estimates put the rate in the Milky Way at roughly 1 every 10 years or so, but they are almost never observed at this stage. There are 2 windows in which a merger can be studied, and the blue ring falls between them. The first window is the merger itself, which produces a brief brightening called a luminous red nova. Those have been caught, most famously V1309 Scorpii in 2008, where archival survey data turned out to have recorded the 2 stars spiraling inward for years before they finally touched. But after that flare, the merged object buries itself in dust and becomes opaque for centuries. The second window is thousands of years later, when the remnant has settled into whatever it is going to be, and the evidence of what happened has dispersed. The Blue Ring Nebula sits in the gap, old enough for the dust to have cleared, young enough that the debris is still visibly in flight, and the central star is still adjusting to having absorbed another star, not yet arrived at whatever equilibrium it is heading toward. X-ray observations reported in 2022 added to that picture, showing an object that is still settling. The infrared excess around the star fits the same story. Material that did not escape has settled into a disk, which is exactly what a merger should leave behind. It is worth appreciating what the 16 years actually consisted of, because the story is usually compressed into a sentence. It was not 16 years of the object sitting untouched. It was 16 years of active work, proposals written, telescope time requested and granted and used, spectra taken, models built and tested and discarded. Ultraviolet, optical, infrared, spectroscopic, and eventually X-ray data from ground-based observatories and from space, accumulated on one faint circle around one unremarkable star. Every dataset ruled something out, and none of them ruled anything in, until there was enough of a shape to the negative space that the right answer became visible. And this is the only known example. Not because such events are rare, because they are not. Because the alignment required is extreme. The cone axis has to point almost exactly at Earth. Tilt it a few degrees and the circle becomes an ellipse. Tilt it further and it becomes a smear of faint ultraviolet emission that no survey would flag as interesting. Every other stellar merger currently in this phase, and there should be a considerable number of them scattered through the galaxy, is presumably out there right now, oriented some other way, looking like nothing at all. So there is a category of object here that exists in quantity, is visible in principle, and has exactly one confirmed member. The other members are not hidden by distance or dust or faintness. They are hidden by the angle they happen to be sitting at. That collision left debris we can still watch. The next kind of ending leaves nothing to watch at all. Not a remnant, not a corpse, not even a black hole. Number 6. The stars that erase themselves completely. Every star is a standoff between two forces. Gravity pulls inward, trying to collapse the star under its own enormous weight. Radiation pressure from the light produced by fusion pushes outward. For most of a star's life, the two are balanced, and that balance is what a star is. Change either side, and the star adjusts until they match again. In a very massive star, the light itself eventually becomes the problem. Above roughly 1 billion degrees, the gamma rays produced in the core carry so much energy that when they pass close to an atomic nucleus, they can convert directly into matter. A gamma ray disappears, and in its place there is an electron and a positron, a particle and its antiparticle, created out of pure energy, exactly as the relationship between mass and energy allows. That conversion is a catastrophe for the standoff, and the reason is simple. A gamma ray that has become two particles is no longer a gamma ray. It has stopped pushing. So the radiation pressure holding the star up is being converted into mass. And mass falls. The core contracts. Contraction raises the temperature. Higher temperature produces more energetic gamma rays. More energetic gamma rays produce more pairs. More pairs remove more pressure. Each step makes the next step worse, and the star's own support system is now consuming itself, faster and faster. The collapse compresses the core until oxygen ignites, not gradually, in a shell, the way it does in a normal star, but explosively, across the entire core at once. In a star between roughly 130 and 250 times the mass of the Sun, the energy released by that runaway exceeds the star's own gravitational binding energy. Not marginally, by an enormous margin. And that changes the character of the ending entirely. An ordinary supernova blows the outer layers of a star into space and leaves the core behind, as a neutron star or a black hole. There is always a remnant. The star dies, and something remains at the site to mark it. Here, there is no remnant of any kind. The star is not blown apart around a surviving center. It is completely unbound. Every atom is dispersed into space. No neutron star. No black hole. Nothing is left behind at all. The explosion can produce tens of solar masses of radioactive nickel-56, and that is a staggering figure in context. An ordinary core collapse supernova produces a fraction of a single solar mass. The decay of all that nickel powers a light curve that can outshine an entire galaxy for months and take years rather than weeks to fade. There is a narrower mass window just below that range, and it has its own strangeness. Between roughly 70 and 130 solar masses, the pair instability triggers, but the resulting explosion is not quite strong enough to unbind the star. So the star ejects a shell of material, settles, contracts, heats up, and does the whole thing again. That is called pulsational pair instability, and it produces a star that partly explodes repeatedly, throwing off shell after shell over intervals ranging from years to millennia, until it finally collapses for good. And when a later shell catches up with an earlier one, the collision of the two produces enormous brightness. That is one of the leading explanations for the most luminous supernovae ever recorded. The efficiency of what happens in that core is worth putting in perspective, because it explains why the process runs away so completely. Hydrogen fusion, the reaction that powers the Sun and every ordinary star, converts about 0.7% of the mass involved into energy. It is a famously inefficient process that happens to be very good at running slowly for billions of years. Matter and antimatter annihilating convert 100%. Every gram becomes energy. The gap between those two numbers is why a star can spend 10 billion years burning steadily and then unmake itself in a matter of seconds. The energy released in a full pair instability supernova can exceed 10 to the 53rd ergs against around 10 to the 51st for a normal core collapse event. That is roughly 100 times more, released by a mechanism that is fundamentally different from the collapse that produces ordinary supernovae. There is also a requirement about the star's composition that constrains where these can happen. The star has to be metal poor, made of gas with very few elements heavier than helium. The reason is that metal-rich stars lose mass rapidly through stellar winds. Heavier elements absorb light efficiently, so the outer layers of a metal-rich star catch the radiation streaming out from below and are pushed away. A star that starts at 200 solar masses in a chemically enriched environment will have shed itself down well below the pair instability threshold long before it reaches the end of its life. It never gets the chance. Finding a confirmed example has been considerably harder than working out the theory, and the history is instructive. In 2007, a supernova called SN 2006GY in the galaxy NGC 1260 was the brightest supernova recorded to that point. Roughly 100 times more energetic than a typical one. Pair instability in a star of around 200 solar masses was proposed as the explanation, and it was a natural fit, an extraordinary explosion demanding an extraordinary star. That reading held for more than a decade. Then, in 2019 and 2020, a team led by Anders Jerkstrand identified something in spectra that had been taken more than a year after the explosion, emission lines of neutral iron. Those lines had never been seen before in any astrophysical nebula. Neutral iron, iron that has kept all its electrons, is not what you expect in a supernova, where the energies involved usually strip one or several electrons from every atom present. And producing those lines required around 0.3 solar masses of iron, expanding at 1,500 kilometers per second. Working through what could produce that, the team found that only one mechanism was consistent with all of the observations. An ordinary thermonuclear supernova, a white dwarf, the same class of object we have already met twice on this list, detonating inside a dense shell of material that had been ejected less than a century before the explosion. The brightest supernova known was a small dead star in a very large costume. The shell it exploded inside was what made it bright, and the shell had to have been thrown off shortly beforehand, probably through violent interaction with a binary companion. That correction is worth stating clearly rather than skipping past, because it is how the field actually works. A reasonable interpretation held for over a decade was tested by a new kind of measurement and was overturned. Nothing was hidden and nobody was careless. The evidence simply arrived later than the explanation did. SN 2007bi, announced in 2009, was another leading candidate, and it too remains contested. The strongest case now is a supernova called SN 2018 IBB, described in detail in 2024 by Steve Schultze and colleagues after 1,100 days of continuous monitoring, 3 years of watching one explosion fade. Its light curve and its spectra require between 25 and 44 solar masses of freshly created nickel-56. That points to the death of a metal-poor star with a helium core of 120 to 130 solar masses. It is described, carefully and deliberately, as the best pair instability candidate to date. Not as a confirmation. The distinction matters, and the researchers were careful to maintain it. The reason all of this matters reaches back to the very beginning of everything. The first generation of stars formed from gas containing no heavy elements at all, just hydrogen and helium, because nothing else existed yet. And without heavy elements, a collapsing gas cloud cools inefficiently and fragments less readily, which means the stars it produces are expected to be far more massive than anything forming today. So pair instability supernovae may have been common in the early universe. Which means the chemical fingerprint they leave behind, a distinctive pattern in the relative abundances of elements with certain characteristic gaps, is something astronomers actively hunt for in the oldest surviving stars in the galaxy. Find that pattern in an ancient star, and you have found the ashes of one of the first stars, still incorporated in something that is still burning. There is one more test, and it is being run continuously. Because pair instability destroys stars in that mass range entirely, no black holes should ever form with masses between roughly 65 and 120 times the Sun. That is a hard prediction, a forbidden gap in the mass distribution. Gravitational wave detectors have been checking it merger by merger every time two black holes collide anywhere in the observable universe and the ripple reaches Earth. That is an ending with no remainder. The next one has no ending at all. It is a star that is being eaten a little at a time, and it comes back for the next bite every 114 days. Number 5. The star that is being eaten on a schedule. When a star passes too close to a supermassive black hole, it comes apart. The mechanism is straightforward. Gravity weakens with distance, so the side of the star nearer the black hole is pulled harder than the side further away. If the difference between those two pulls exceeds the star's own gravity holding it together, the star stretches, and then it stops being a star. The material spirals inward, heats up through friction, and produces a flare that can outshine the entire center of the host galaxy for months. These are called tidal disruption events, and for as long as they have been observed, they have been understood the same way. A star wandered too close. It was destroyed. That was the end of it. A single event, never repeated, because there was nothing left to repeat it with. ESO 253 is a galaxy about 570 million light-years away in the southern constellation Pictor. It is a merging system, two galaxies in the process of becoming one, with an active nucleus at its center. In November of 2014, the All-Sky Automated Survey for Supernovae recorded a flare from that galaxy's center. It was catalogued as ASSN 14KO, filed as an ordinary flare from an active galaxy and not pursued. Active galaxies flare. It is what they do. In 2020, Anna Payne, then a graduate student at the University of Hawaii at Manoa, went back through 6 years of accumulated survey data on that galaxy. She found 17 flares. And when she measured the spacing between them, they were separated by 114.2 days. Evenly. Predictably, like a metronome. That regularity is the entire story, and it is worth being clear about why. Astronomical transients are not predictable. A supernova goes off when it goes off. A gamma-ray burst arrives without warning. The entire discipline of studying these events is a discipline of reacting quickly, of alert networks and rapid response telescopes and observers being woken up at 3 in the morning to point something at a patch of sky before the event fades. Payne's team calculated when the next flare from this galaxy should occur and asked observatories to be pointed at it in advance. The flare arrived on schedule. They did it again. And again, it became the first flaring galactic nucleus whose outbursts could be booked in a calendar, observed at will, with instruments across the electromagnetic spectrum already in place and already recording before anything happened. Space-based ultraviolet and X-ray observatories coordinated with ground-based optical telescopes, all watching, all waiting for something they knew was coming. The favored explanation is a repeating partial tidal disruption. A star is in a highly eccentric orbit around the central black hole, with a period of about 114 days. At each closest approach, the black hole's tides strip material off it, an amount roughly equal to 3 times the mass of Jupiter every pass. That material falls inward, heats, and produces the flare. But the star is not destroyed. The encounter is not quite close enough for that. It survives, swings back out along its long elliptical path, and returns 114 days later to lose another piece of itself. It has done this at least dozens of times within the observed record. It has presumably been doing it for very much longer than anyone has been watching. Follow it through one pass. It comes inward on the long stretch of its orbit, gathering speed, the way anything does when it falls. Ahead of it, the accretion disk around the black hole begins to brighten. The near side of the star starts to feel a stronger pull than the far side, and the difference grows quickly as the distance closes. The star deforms, stretched along the line toward the black hole, compressed across it. At closest approach, the outer layers lift away entirely, a stream of material peeling off and falling inward on a path the star itself will not follow. 3 Jupiters of it, gone. Then the star, misshapen and lighter than it was, passes through the bottom of its orbit and begins the long climb back out into the dark, where it will spend the next several months slowly slowing down, turning around, and starting back. 3 Jupiter masses per pass is a figure that deserves a moment, because it sounds modest and is not. Jupiter is about 1,000th of the Sun's mass, so 3 of them is around 3,000ths of a solar mass per encounter. But there are roughly 3 encounters a year, and the process has been running for far longer than the 6 years of survey data that revealed it. Over even a few thousand years, that adds up to a substantial fraction of a stellar envelope. Whatever this star was when it first fell into the orbit, it is measurably less now. The host galaxy is worth a note too. ESO 253 is a merger remnant, and it has 2 nuclei, 2 galactic centers, still in the process of combining. The flaring one is the more massive. That is not a coincidence, and it is probably part of the explanation. Galaxy mergers stir up the orbits of stars near the center, and a stirred-up nuclear region is very efficient at delivering stars onto paths that bring them close to a supermassive black hole. The conditions that produce this kind of encounter are the conditions of a galaxy in the middle of being rearranged. There is one detail that gives the whole thing an ending. The period is not perfectly constant. Measurements show it getting shorter with each cycle, by around 0.0026 days per orbit. That is a small number, but it is measured with confidence, and it means the orbit is decaying. The star is spiraling inward, which means this stops eventually. The encounters will get closer and more violent. More material will be stripped each time, and at some point, a pass will take more than the star can survive. The routine will become an event, and then it will be over. The flares themselves are not simple. Detailed monitoring published in 2023 found repeated bumps and rebrightenings within individual outbursts, which suggests the stripped material does not simply fall straight in. It has to circularize first, settle into orbit around the black hole before it can accrete, and that process happens in stages, each one visible as a separate feature in the light curve. How a star ends up in an orbit like that is its own question. The leading idea involves a binary star system that approached the black hole and was torn apart by tides, with one member captured into a tight orbit while the other was flung away at enormous speed. Alternative models involve gradual orbital evolution through interactions in the crowded star cluster that surrounds any galactic nucleus. And this object is no longer alone. Other repeating partial disruption candidates have been identified since: AT 2020 VDQ, AT 2021 AEUK, and others, and a systematic search for more is underway, which has an uncomfortable implication for the archives. Ordinary complete tidal disruptions are estimated to happen roughly once every 10,000 to 100,000 years per galaxy. That is why finding one that repeats every 4 months was so unexpected. But it also means that some meaningful fraction of the flares astronomers have been recording for decades and filing as ordinary activity from active galaxies may not be ordinary activity at all. They may be individual bites taken out of stars that are still alive. The image that survives is precise, and it is not a death. It is a routine. There is a star on a repeating orbit that carries it, roughly every 4 months, close enough to a supermassive black hole to lose a piece of itself. Then it carries it back out into the dark to wait. It has been doing this for longer than there have been people to notice, and it has not yet lost enough to stop. That star's schedule is known to within a day. The next object has been keeping a schedule of its own since 1950, and nobody can say whether it is one star or several million suns worth of black hole. Number 4, the thing that has been erupting since 1950. About 90 million light-years away, in the constellation Ursa Major, there is a dwarf galaxy called Markarian 177. Off to one side of its center, displaced by roughly 2,600 light-years, sits a bright, compact source. It is catalogued as SDSS 1133. In 2014, a team led by Michael Koss, then at ETH Zurich, published an analysis that reached back into the photographic record. And SDSS 1133 appears in images going back to 1950. It has been continuously detectable for more than 6 decades. And at points during that span, it did not fade at all. It got brighter. That duration is the problem, and it is the whole of the problem, because there are only 2 things this object can plausibly be, and both of them are extraordinary. The first possibility is that it is a supermassive black hole that has been thrown out of its galaxy. When 2 galaxies merge, their central black holes eventually spiral together and merge as well, and that final coalescence radiates gravitational waves, a great deal of them, in a very short time. If the emission is asymmetric, and it will be unless the 2 black holes happen to be identical in mass and in spin, then the waves carry away net momentum in one direction, and the merged black hole recoils in the other. The kick can be enormous. Theoretical calculations put the largest recoil velocities at approaching 5,000 kilometers per second, which is more than enough to eject a black hole from a galaxy entirely. It would leave dragging a small quantity of gas with it, whatever was bound tightly enough to come along, and that gas would continue to fall inward and glow for as long as it lasted. Markarian 177 shows disturbed structure consistent with a recent merger. and the displacement of SDSS 1133 from the galaxy's center fits what an ejected object would look like. It is a dwarf galaxy, which helps the case. Dwarf galaxies have low escape velocities, so it takes less of a kick to remove something from one. The second possibility is that it is a single star. Luminous blue variables are among the most massive stars known, and they are violently unstable. They undergo what are called giant eruptions, in which they shed enormous quantities of material, sometimes many solar masses, without actually dying. Eta Carinae in our own galaxy did this in the 1840s. It brightened until it was briefly one of the brightest stars in the sky, threw off something like 10 solar masses of material, and survived. It is still there. On this reading, SDSS 1133 is a star of that kind, in an eruptive phase that has been running since before 1950. Which would make it the longest such outburst ever documented, by a wide margin. Eta Carinae's great eruption lasted roughly a decade. And it would mean the star has since finally exploded as a supernova. The evidence has not settled the question, and the reason it has not is that it points both ways. Hubble ultraviolet observations have been obtained. Ground-based spectroscopy has been carried out. SWIFT, with its rapid response ultraviolet and X-ray instruments, has been pointed at it. Follow-up work published in 2022 found evidence in the historical record of multiple giant eruptions, separated in time. That favors the star, because repeated eruptions are exactly what luminous blue variables do, and are not an obvious behavior for accreting gas around an ejected black hole. The same work found X-ray emission from the source. That favors the black hole because accretion onto a massive compact object produces X-rays naturally, and a stellar eruption does not, at least not easily. So the two strongest pieces of recent evidence support opposite conclusions. The displacement itself sits in an awkward middle ground, which is part of why the case is hard. About 800 parsecs from the galaxy's center is far too far for an ordinary active nucleus. Those sit at the center by definition, because that is where the black hole is. But it is not so far that the object must be unbound. It could be a black hole that was kicked hard enough to be thrown out of the middle, but not hard enough to escape entirely, and is now on a long, slow orbit that will eventually bring it back. That would be its own remarkable thing, a galactic center that has temporarily misplaced its center. Gravitational wave recoil, meanwhile, was predicted from general relativity long before anybody had observed two black holes merging directly. It came out of the mathematics, a consequence of the asymmetry in how the waves are radiated, and it sat as a theoretical curiosity for decades. The detection of merging black holes has since confirmed the framework that predicts it. What has not been confirmed is any individual case of the recoil having actually happened to a supermassive black hole, which is exactly what makes candidates like this one valuable and exactly why the standard of evidence is high. There is a way to settle it, and it requires only time. If the object is a recoiling black hole, it will still be there indefinitely, and its spectrum should eventually show the broad emission lines produced by gas orbiting at high speed around a massive compact object. If it was a star that finally exploded, it should now be fading, and continued monitoring will show that. Observations continue. It is a familiar shape by now. AR Scorpii sat in a catalogue for 45 years, described as an ordinary variable star. The pulsars that switch off were whispering below the detection threshold for 2 decades. And here is an object that has been on photographic plates since 1950, bright enough to record, in a galaxy close enough to study, and the identification of what it actually is has not been made in 76 years. Only a handful of recoiling supermassive black hole candidates have ever been proposed, anywhere. None is confirmed beyond dispute. If this one is real, It is direct evidence of something that has only ever been calculated, a black hole of millions of solar masses, evicted from the galaxy that made it by the recoil of ripples in space-time. But what puts this object at number 4 is not which answer turns out to be correct. It is that the two candidates are so completely different and that the question has stayed open for so long. One possibility is a black hole containing millions of stars' worth of mass, traveling away from its own galaxy at a speed that would cross the Earth's diameter in a few seconds. The other is a single star that has been in the process of tearing itself apart since before most people alive today were born, and has done it in stages, and may only recently have finished. Astronomers have a bright, well-studied object at 90 million light-years. They have photographs of it from 1950. They have ultraviolet data, optical spectra, and X-ray measurements. 4 generations of astronomers have looked at it. And it is still an open question whether it is one star or a black hole made of millions of them. The photographic plates that establish the 60-year history are worth a word of their own because they are the reason any of this is answerable. They come from sky surveys carried out decades before digital detectors existed, glass plates coated with emulsion, exposed for hours at telescopes, developed by hand and then stored in cabinets. Somebody had to decide to keep them. Somebody had to catalogue and preserve them through the transition to digital astronomy when they served no immediate purpose. And because they did, there is a continuous record of one anonymous point of light in a small galaxy, stretching back 3/4 of a century, waiting for a reason to be looked at. 2 answers, both extraordinary, neither settled. The next object had its answer hiding in the travel time of light, and the person who found it was not an astronomer. Number 3. The ghost of a quasar that switched off. In July of 2007, a Dutch schoolteacher named Hanny van Arkel signed up for a new website called Galaxy Zoo. The premise of the project was simple and slightly humbling for the people running it. Computers at the time were poor at classifying the shapes of galaxies. Humans were very good at it. The pattern recognition involved is something the visual system does effortlessly, and algorithms then struggled with. So a group of astronomers put images from the Sloan Digital Sky Survey online, wrote a short tutorial, and asked members of the public to sort them. Hundreds of thousands of people volunteered. The servers struggled to keep up in the first days. Van Arkel taught music. She had no astronomical training. She was working through her assigned images, spiral, elliptical, spiral, edge-on, merger, when she came to a picture of a spiral galaxy called IC 2497, and there was something next to it. A large, irregular blob, glowing an unusual green. Unattached to the galaxy, and unlike anything in the classification guide, she posted about it on the project's forum and asked what it was. Nobody knew. The astronomers running the project did not know either. And because her forum post had used the Dutch word for object, the thing acquired a name that has stuck ever since, Hanny's voorwerp. Here is what it turned out to be. IC 2497 is around 650 million light-years away. The voorwerp is roughly the size of the Milky Way, a cloud of gas tens of thousands of light-years across. Its green color comes from doubly ionized oxygen, which is a very specific signal. To strip 2 electrons from an oxygen atom requires photons of high energy, and a great many of them. Ordinary starlight cannot do it. Something had to be blasting that cloud with intense high-energy radiation. The obvious candidate was the galaxy sitting right next to it. IC 2497 should have contained an active supermassive black hole, a quasar, pouring out more than enough radiation to light the cloud. Except it does not. Observations across the spectrum, including with Hubble and with X-ray telescopes, showed a galactic nucleus that is quiet. There is a black hole there. It is not doing anything close to what would be required. The energy needed to make the Vorwerp glow the way it glows is simply not being produced. The resolution is in the travel time, and it is the kind of answer that reorganizes how you think about looking at anything. The Vorwerp sits tens of thousands of light-years from the galaxy's core. Light takes tens of thousands of years to cross that distance. So the radiation currently illuminating that cloud left the center of the galaxy a very long time ago. Which means the Vorwerp is not showing what the quasar is doing. It is showing what the quasar was doing. The quasar switched off. Analysis by a team led by Kevin Shawinski at Yale, published in 2010, concluded that the shutdown happened within the past 200,000 years, and most likely far more recently than that, possibly within the last 70,000. The Vorwerp is a light echo, a cloud still lit by a source that has already gone dark, glowing on borrowed light that has not yet finished arriving. That result mattered enormously, and for a reason that has nothing to do with how strange it looks. Quasars were understood to fade gradually. The picture was that a supermassive black hole consumes the gas available to it, the supply gradually thins, and the output declines over millions of years. It was a reasonable assumption, and there was no way to test it, because nobody can watch a quasar for 1,000,000 years. The Vorwerp put a clock on it. It says that one quasar shut down in far less than 1,000,000 years, that the decline happened on a timescale of tens of thousands of years, which in this context is close to abrupt. Feeding a supermassive black hole is apparently something that can stop almost without warning. That is now a measured property of these objects, rather than an assumption, and the measurement came from a cloud of gas that was still lit up after the light was turned off. It is worth being concrete about how bright that former quasar was, because the phrase gets used loosely. The luminosity required to produce the ionization seen in the Vorwerp puts IC 2497, at the time the light left it, in the range of genuine quasars, meaning that until geologically recently, this galaxy was among the brightest objects in its part of the universe. A single point at its center was outshining every one of its hundreds of billions of stars combined. And now it is quiet, and the only remaining evidence is a cloud of gas that has not yet received the news. There is also a straightforward physical reason the light echo works as a measurement, and it is worth spelling out. Light travels at a fixed speed. So distance is time. A cloud at 10,000 light-years from the source is showing conditions from 10,000 years ago. A cloud at 50,000 light-years is showing conditions from 50,000 years ago. If a single extended structure is lit unevenly, bright where the radiation has arrived, dark where it has not, then the boundary between the two is a snapshot of the moment the source changed. You are reading a light curve written across space instead of across time. Hubble imaging in 2011 added more. The Vorwerp contains a distinct hole, a cavity in the gas roughly 20,000 light-years across, which appears to have been carved by an outflow from the galaxy's nucleus. And the Vorwerp itself is only the brightest part of a far larger structure, a streamer of gas stretching some 300,000 light-years around IC 2497, most likely pulled out of the galaxy during an interaction with another one. The cavity in the gas is its own detail worth holding. 20,000 light-years of empty space, punched through a cloud by an outflow from the galaxy's center. That is not the radiation doing the work. That is material, a jet or a wind of particles, physically clearing a channel. So the galaxy did two things to that cloud. It lit it from a distance with radiation that is still arriving, and it drilled a hole through it with something moving considerably more slowly. The two effects are visible in the same image, recording two different events at two different times. The discovery also created a search. Once astronomers knew what the signature looked like, Galaxy Zoo volunteers went hunting for more of them, and found over 20 smaller examples. They are called vorwerpjes, little vorwerps. The whole class is now used as a tool for measuring how quasars turn on and off, and surveys have found that a substantial fraction of nearby active galaxies show signs of having been considerably brighter in the geologically recent past. The Vorwerpjes survey produced a number that reframes the whole subject. Among the nearby active galaxies examined, something like 1 in 5 showed an ionization echo, evidence that the galaxy had been substantially brighter in the recent past than it is now. That is not a handful of oddities. That is a common condition. It suggests that the output of a supermassive black hole is not a steady state that slowly declines, but something that swings up and down over tens of thousands of years, and that any given galaxy caught today is likely to be somewhere in the middle of a swing, rather than at a stable level. Which means the sky is full of these. Every galaxy that has recently dimmed has, in principle, a shell of gas around it still lit by the brighter version of itself. Most of those shells are too faint to see, or too diffuse, or there is no convenient cloud in the right place to catch the light. The Vorwerp is visible because a large streamer of gas happened to be positioned exactly where the radiation would hit it, at exactly the right distance for the timing to work out. So the object is a research instrument now. But the part of this story that has aged best is who found it. Hanny van Arkel was not an astronomer. She was a music teacher, sitting at a computer in the evening, clicking through images because a website had asked for help. She noticed something that did not match the guide, and, this is the part that actually matters, she had the nerve to ask about it rather than assuming she had made a mistake. That distinction is worth dwelling on. A very common response to seeing something unexpected in an unfamiliar field is to assume the error is yours. Most people, most of the time, would have moved on to the next image. The object carries her name because she did not. She has since been a co-author on papers about it and has spoken publicly about citizen science. The Vorwerp remains the most cited discovery to have come out of a public classification project. And what she found, on an ordinary evening, at a computer, is a cloud of gas the size of a galaxy, lit by an engine that has already stopped, glowing on light that is still in transit from something that no longer exists. That cloud is lit by an engine that has already stopped. The next black hole is doing the opposite of stopping anything. It is building. Number 2, the black hole that builds stars. The standard account of what a supermassive black hole does to its galaxy is destructive, and it is well supported by a great deal of evidence. When a black hole feeds, it produces enormous radiation and drives powerful outflows of hot gas. Those outflows heat the surrounding material and push it outward, sometimes clear out of the galaxy. And gas that is hot and moving cannot collapse into new stars. Star formation requires cold, dense, quiet gas that is able to fall in on itself under its own weight. Heat it, stir it, or blow it away, and nothing forms. The process is called negative feedback, and it is the leading explanation for one of the largest scale patterns in the universe, why big galaxies stop forming stars. Large elliptical galaxies are full of old red stars and almost no young blue ones. They ran out, or rather, something took their fuel away. On this account, black holes are the reason galaxies die. Henny's 210 is a dwarf starburst galaxy about 30 million light-years away in the constellation Pyxis. It is named for Carl Hennizer, an astronomer who catalogued emission line objects and who later flew as a NASA astronaut aboard Challenger in 1985. It is small, a fraction of the Milky Way's mass, and it is forming stars vigorously. In 2011, Amy Reines, then a graduate student, reported evidence that this small galaxy contains a massive black hole at its center. That was notable on its own. Black holes of that kind were expected in large galaxies, and the prevailing idea was that they grew alongside their hosts through a long history of galactic mergers. Finding one in a dwarf galaxy that has never undergone a major merger raised a genuine question about how such objects form in the first place. The claim was disputed. Some of the observational evidence was also consistent with a supernova remnant, which can mimic aspects of an accreting black hole's signature. The question stayed open for about a decade. In January of 2022, Zachary Schutte and Amy Reines, both at Montana State University, published Hubble observations that settled it, and that answered a different question at the same time, one nobody had asked. Because Henise 210 is close enough for Hubble to resolve fine detail, they were able to trace an ionized filament running from the black hole's location outward to a region of recent star formation. A bridge of glowing gas, roughly 500 light-years long, connecting one to the other. Then they took spectra along that filament, measuring the velocity of the gas at points all the way down it. The velocities traced out a sinusoidal pattern, a smooth wave, back and forth along the length of the structure. That pattern is a signature, and it has a specific cause. It is what you get from a precessing bipolar outflow, a jet coming out of the black hole, wobbling as it goes, sweeping out a corkscrew shape in space. Nothing else easily produces that particular velocity structure, which is why it was the decisive piece of evidence. And at the far end of the filament, where the outflow terminates, there is a cluster of young stars. The team measured the speed of the outflow and the ages of those stars, and the two numbers line up. The outflow arrived first. The stars formed afterward. The order of events is fixed by the clock, which is what turns a coincidence into a causal claim. What happened is that the outflow, traveling at something like 2 million kilometers per hour, struck a dense molecular cloud and spread out along its surface, the way water from a hose flattens when it hits a mound of earth. And the impact compressed the gas rather than dispersing it. Compressed gas is exactly what star formation needs. The cloud collapsed and produced stars. This is positive feedback. The black hole is causing star formation rather than preventing it. It is doing the opposite of the thing black holes are known for. And the difference appears to be a matter of scale, which is the elegant part. In a large galaxy, the central black hole is enormous, millions or billions of solar masses, and the outflows it drives are correspondingly violent. They blast gas out of the galaxy entirely and shut everything down. In a dwarf galaxy, the black hole is proportionally much smaller, so the outflow is gentler and more diffuse. The same physical process, a jet of hot gas hitting a cloud, produces the opposite outcome because it squeezes rather than destroys. The difference between building and destroying is a question of how hard you push. The black hole in Henise 210 is estimated at roughly 1 million solar masses. That is about a quarter of the mass of the Milky Way's central black hole, sitting in a galaxy vastly smaller than ours. And the filament connecting it to the star-forming region is around 150 parsecs long, which is only resolvable at all because the galaxy is relatively nearby. At any greater distance, the whole structure would be a single unresolved blur. Follow-up work has extended the result. A study in 2025 examined additional starburst dwarf galaxies and found evidence that positive feedback from black holes may be enhancing star formation across this class of galaxy more broadly, which suggests Henise 210 is not a fluke but a representative case, and that a whole category of small galaxies is being helped along by the objects we associate with endings. The star cluster at the end of the filament is only a few million years old, which is what makes the timing argument as tight as it is. Stars announce their ages fairly clearly through their colors and masses. The most massive ones burn out fast, so a cluster that still contains them has to be young. A few million years is the blink of an eye against the age of a galaxy, and it means the sequence of events is not a matter of inference across long timescales. The outflow traveled, arrived, and the stars appeared, all within a window short enough to measure. There is a second implication in the original discovery that should not be lost. If a massive black hole can exist at the center of a galaxy that has never undergone a major merger, then the standard growth story, black holes assembling gradually through repeated galactic collisions, cannot be the only route. Something else must be able to produce them. The leading alternative is direct collapse, a large cloud of gas in the early universe, falling in on itself and forming a massive black hole immediately, without ever passing through the stage of being a star. Henise 210 is evidence that whatever that process is, it happens, and it happens in small galaxies. There is a longer implication, and it reaches back to the early universe. The early universe was full of small galaxies. Large galaxies had not been assembled yet. They were built up over billions of years out of smaller pieces. So if black holes in small galaxies build stars rather than suppressing them, then the black holes in the very first galaxies may have been contributing to star formation at precisely the epoch when galaxies were coming together. Which would mean the standard picture, black holes as the things that end star formation, is a description of the mature universe, not the young one. It is what happens once galaxies get large. In the era when everything was being built, the same objects may have been doing the building. Dwarf galaxies are useful for exactly this reason. They have undergone fewer mergers and less processing than large galaxies, so they preserve conditions closer to the early universe than anything else nearby. Henise 210 is 30 million light-years away, which is close enough to study in detail, and it is showing something that otherwise could only be inferred from objects billions of light-years off. The dead are not finished. We have followed that through this list. A stripped stellar core still orbiting the thing that stripped it, a star that survived its own supernova and came back brighter. And here it arrives at the end of its arc. A black hole, the most complete ending physics offers, an object defined entirely by what it takes in and never gives back, is the reason a cluster of stars exists. A black hole that makes stars rather than ending them. And at the top of this list is the one that does nothing but consume, the brightest thing anyone has ever seen, which sat in our own photographs for 44 years while our instruments insisted it was not there. Number 1. The brightest object in the universe, which we filed as a star. In February of 2024, a team led by Christian Wolff at the Australian National University announced the identification of a quasar catalogued as JO529 4351. It is the most luminous object ever observed. Not the most luminous quasar. The most luminous object of any kind, anywhere, that anyone has ever found. The numbers need unpacking one at a time, because taken together, they refuse to sit properly in the mind. The black hole powering it has a mass of about 17 billion times the Sun. For comparison, the black hole at the center of the Milky Way is around 4 million solar masses. This one is more than 4,000 times larger than that. It is consuming material at a rate of roughly 1 solar mass per day. Not 1 sun per year, or per decade, or per century. 1 entire star's worth of matter every 24 hours, continuously. And it has been doing that, or something like it, for long enough to accumulate 17 billion solar masses. At that rate, it gains around 365 solar masses in a year, the mass of a small star cluster every few centuries. The material does not fall straight in. Anything approaching a black hole with the slightest sideways motion goes into orbit rather than diving, so the infalling matter forms a disk. Friction within that disk, layers rubbing against layers at different speeds, heats it enormously, and that heat is what produces the light. The disk around this black hole is approximately 7 light-years across. Sit with that for a moment. Light takes 7 years to cross it. The nearest star to the Sun is a little over 4 light-years away, and the distance to it is something that reasonable people describe as unreachable, and that our fastest spacecraft would take tens of thousands of years to cover. This single structure, one disk of hot gas, around one black hole, is nearly twice as wide as the entire distance between the Sun and its nearest neighbor. The output of that disk is around 500 trillion times the luminosity of the Sun. That is not a comparison to a bright star. The Milky Way contains several 100 billion stars, and this one object outshines the whole galaxy by a factor of thousands. Walk outward through it, since nothing ever will. At the center is the black hole itself, and its event horizon alone is larger than most planetary systems. Move outward and you are in the inner disk, where the material is hottest and moving fastest, orbiting at an appreciable fraction of the speed of light and radiating fiercely enough that the light itself pushes back on the gas. Keep going. The disk cools as it widens. The outer regions run at something like 10,000 degrees, which is hotter than the surface of most stars, and this is the cool part. Keep going further and further, and after you have traveled the entire distance from the Sun to Proxima Centauri, you are still not at the edge. Go the same distance again, and roughly then you reach the outer rim. There is no direction you could look in that would be dark. And somewhere in that structure, at any given moment, a sun's worth of material is completing its fall. The light we are seeing has been traveling for about 12 billion years. The universe was under 2 billion years old when it left, an eighth of its present age. So none of this is a description of something happening now. It is a description of what was happening when the universe was very young, and whatever that black hole became in the 12 billion years since is not knowable from here and never will be. All of which would make it a remarkable discovery on its own. What makes it belong at the end of this particular list is how it was found. JO 529 was photographed in 1980 on plates from the European Southern Observatory's Schmidt Southern Sky Survey. It has been sitting in astronomical archives for more than 4 decades. It is bright enough that a reasonably equipped observatory can see it without difficulty. It appeared in multiple later surveys as well, and was catalogued repeatedly. It was never hidden, never faint, never obscured. Modern sky surveys produce far more data than any human being can examine. So the sorting is done by machine learning models, trained to distinguish quasars from stars and galaxies and everything else in the images. And those models learn from objects that are already known. A model trained on a catalogue of previously discovered quasars has learned, implicitly and without anyone intending it, how bright a quasar is allowed to be. When the data for this object went through the Gaia mission's classifier, the algorithm assigned it a 99.98% probability of being an ordinary star in the Milky Way. Not a low-confidence guess. Not a flag for human review. Near certainty, and completely wrong. The reason is straightforward once it is stated. The object was too bright to be a quasar, according to a system whose entire understanding of quasar brightness came from the quasars that had already been found. Presented with something more luminous than anything in its training data, the model did the only thing available to it. It concluded the object must be something else. Something nearby, something ordinary, something that fits. Astronomers later noted that a human being looking at the same Gaia spectrum would have recognized it as a quasar immediately and read off its distance at a glance. The information was all there. Nothing was ambiguous. The spectrum was not subtle. There is a phrase for this in machine learning, and it is not a criticism of anybody's work. A model can only recognize what it has been shown. Train a system on every quasar in the catalogue, and it will become excellent at identifying quasars that resemble the ones in the catalogue. It will also become confident, quietly, invisibly confident, that quasars do not exceed the brightest example it was given. Nobody wrote that rule. Nobody decided it. It emerged from the data, and it was applied with 99.98% certainty to the most luminous object in the observable universe. Objects like this one are genuinely rare. The team's search covered large areas of sky and expected only a handful of comparably luminous quasars to exist at all. Which means the failure mode compounds. The rarer something is, the less likely it is to appear in any training set, and the more confidently it will be rejected when it finally turns up. It was found in the end because the team at the Australian National University went looking specifically for bright quasars that automated methods might have rejected. They used a modest 1.3-meter telescope at Siding Spring Observatory in Australia, followed by the 2.3-meter telescope for the initial spectrum, and then the very large telescope in Chile to measure the mass and the accretion rate properly. They went hunting for the thing the machines would refuse to see, and this was the first place they looked. And that is the shape of this whole list, arriving at the end. Chariklo's rings existed for however long they have existed before 7 telescopes happened to catch a shadow lasting less than a minute. AR Scorpii sat in a catalogue for 45 years marked as an ordinary variable star and was found by amateurs watching a boring object. The pulsars that switched themselves off were whispering below the detection threshold for 2 decades. SDSS 1133 has been on photographic plates since 1950 and still has no agreed identification. The star being eaten every 114 days was in a survey archive for 6 years before anyone measured the spacing between the flares. The Blue Ring Nebula waited 16 years. Hannes Voorwerp was found by a music teacher clicking through images in the evening. And the brightest object in the known universe was in our photographs for 44 years, and the tools built to sift the sky looked directly at it and reported, "Nothing here, just a star." None of these things were hiding. Every one of them was in the data, recorded, catalogued, preserved, waiting for someone to look at it in a way the existing categories did not permit. That is what the pattern actually is, and it is worth naming clearly because it is more interesting than any single object on the list. Every rule that failed here was a good rule. The Roche limit is correct physics. The models of stellar engulfment are sound. The understanding that supernovae destroy the stars that produce them was built from a great deal of careful work and is right in the overwhelming majority of cases. The classifier that rejected the brightest quasar in the universe was not broken. It was working exactly as designed, doing precisely what it was built to do. The limits were not wrong. They were just written first. And that is the position anyone is in who looks at the sky or at anything else. The tools for recognizing something new are assembled entirely out of the things already known, which works, almost always, and quietly guarantees that the most unusual object in any collection is the one most likely to be sorted into the wrong pile. So the honest question at the end of this list is not about the quasar. It is about what is currently sitting in the archives, already photographed, already measured, already catalogued under something ordinary, because the only instruments available for sorting it were built out of what came before. The plates are still there. The survey data is still there. It is not going anywhere, and neither are the objects. Somewhere in it, almost certainly, is the next thing on a list like this one. It has already been recorded. Somebody has already looked at it and moved on, and filed it as unremarkable, and gone to bed. Sleep well, and good night.